Hi guys, this is going to be a quick short crash course on organic chemistry for O levels, especially for your exams that are happening in July. So I'm going to start off with the first thing, organic. What's the word? What's the meaning of the word organic? So organic chemistry is the chemistry that's related to carbon compounds. Any compound that's made out of carbon, whether it's even glucose, carbon dioxide, carbohydrates, fats, proteins, etc. Lots of molecules are made out of carbon. And why is carbon so important? Because it's all living organisms are made from carbon compounds. We are carbon compounds. Animals are carbon compounds. Plants are carbon compounds. And what happens to dead plants and animals after billions of years of compression? They turn into fossil fuels. So pretty much all fossil fuels, your petrol, your diesel, your kerosene, etc., they're all pretty much carbon compounds. Organic chemistry is one of the most important branches of chemistry because pretty much all your medicine or anything that's related to medicine, agriculture, that's organic, and your petrochemical industry, that's all related to organic compounds. Now, the first thing is, why is carbon so important, especially in the chemistry of life? The reason carbon is so important is that carbon makes four really, really strong bonds. What that means is that if an element is capable of making, because it's a small atom, it makes really strong bonds. So it's very easy to make complicated structures from this. You can't really make complicated structures from elements that can only make one bond or two bonds because the bonding would not be that versatile. You wouldn't be able to make really, really complicated three-dimensional structures. For carbon, that's easy because it can form four very, very strong bonds. Then moving on to that, we've figured out that carbon is important. The next thing we're going to talk about is the structures. You should know that's the first very, very important basic understanding of how to make structures of organic molecules or any molecule, and what are structural formulas. Now, before moving on to that, you should know that group 7 makes one bond. Most of the time they make one bond. So if you have fluorine, chlorine, bromine, or iodine, they usually just make one bond in a molecule. Any element that's a part of group 6, that would usually make two bonds. You've got oxygen and sulfur. Most of the time they're just making two bonds. Group 5 elements, they usually make three bonds because they need 3 electrons to complete the outer shell. They already have 5 valence electrons, so they would need 3 electrons. So they're going to make 3 bonds. So nitrogen and phosphorus are some examples of group 5 elements. And group 4, most of the time they make 4 bonds. And carbon and silicon are an example. So the first very, very basic thing that has to be done is you should know how to draw correct structures. This is very, very important. So what I'm going to do is I'm going to give you some incorrect structures. So for example, the ones that you can see on the screen over here, these are incorrect. Why? Because if I just have this in front of you, this table over here, and one very other important element that is not part of any group. Remember, hydrogen makes one bond always. It only has one electron, so it can only share one electron. That's it. So it's always making one bond. So just coming back to H, remember it's very important because the next, apart from carbon, the most important element in organic chemistry is probably H. So we were focusing on drawing the correct structures. These are known as structural formulas where you show a bond by a dash. So you show a double bond by 2 dashes. So that's the number of electrons that are being shared between atoms. So for example, this molecule over here, this is an incorrectly drawn molecule because over here, for example, look at nitrogen over here. I told you that nitrogen is in group 5 and it's supposed to make 3 bonds. So right now, if you just focus on nitrogen, let me put a tick mark on that. Let's focus on nitrogen. You would notice that it is right now just making 2 bonds. So it should be making a third bond with something. So that something could be, I mean, I can make 3 bonds with carbon. That's it. So now the structure of nitrogen is correct. It's perfectly fine. There's nothing wrong with that. And carbon, how many bonds should carbon make? Should make 4 bonds. So you can see over here, carbon is making 4 bonds, 1 over here and 3 on this side. So this one is also correct. Let's focus on this carbon atom over here. Remember, I'm just doing random things, just trying to figure out how to draw the correct structure. So it's up to you if you want to attach an atom to it. The focus is to make correct structures. So focus on this carbon atom over here. It's making 4 bonds, 2 over here, 1 over here, 1 over here. So that's a total of 4 bonds. Carbon is going to make 4 bonds. This carbon over here is just making 2 bonds over here. That's it. Carbon is supposed to make 4 bonds. So I'm going to just add some random atoms. Let's add an H and an F atom. So I'm just randomly adding atoms. No logic behind that, just to complete the structure. So you can see over here that carbon is at the moment making a total of 4 bonds. 1 with this, 1 with this, 2 with this. And look at hydrogen. It's supposed to make 1 bond. It is making 1 bond. So this carbon is correct. The hydrogens are also correct. And this fluorine is also correct because it was also supposed to make, you can see over here, it was supposed to make 1 bond because it's in group 7. Let's now come to oxygen now. You can see oxygen over here. That's right now making just 1 bond, and oxygen is in group 6. It's supposed to make 2 bonds. So let's add some other atom to it, and I'm going to add an H atom. So I'm just going to pick an H atom and add it to it. Now the oxygen is making 2 bonds. The hydrogen is making 1 bonds. Everything kind of looks it looks fine now. Let's do the same thing, just random. I'm just going to randomly add atoms just to make sure that the structure is correct. So again, starting with this nitrogen, it's supposed to make 3 bonds. Over here, should make 3 bonds. Not making 3 bonds, so we can add an atom over here. Let's add chlorine over here. So this nitrogen is now fine. This carbon is already fine because it's already making 4 bonds. 1 over here, and 2 bonds over here. We can talk about chlorine. Chlorine is in group 7, so it's supposed to make just 1 bond. That's fine. I've got carbon over here, and carbon is supposed to make how many bonds? It's supposed to make 4 bonds over here. So right now it's just making 2 bonds. So what I can do is I can add an oxygen, and oxygen is supposed to make 2 bonds. So that would do the job. This carbon is making 3 bonds at the moment. So we can add a 4th atom over here. Let's add fluorine. TK just randomly picking fluorine. So this carbon is correct. This oxygen is correct. This carbon atom over here is now fine. It's making 4 bonds. The oxygen should be making 2 bonds. So we can add an F. And this oxygen over here should be making 2 bonds as well. So I can add an F atom. And this carbon atom over here is right now making 3 bonds, so I can add the 4th atom, and that could be an H atom. So remember, by just looking at the molecule, first thing is you should know, is the structure incomplete, is the bonding correct or not, and this is very vital. So we can do a few more examples for this. Let's do another example. So here's another example that I'm going to try and solve. So let's start with the first carbon atom. Not complete, just making 1 bond. It's supposed to make 4 bonds, so I can add 3 hydrogens, and that would do the job. It's now the structure is correct. This carbon right now is making 3 bonds, so what I can do is I can add chlorine, and this carbon atom over here is now making 4 bonds. This carbon atom is already correct. It's making 4 bonds. Oxygen is in group 6, should make 2 bonds, and it is making 2 bonds. And nitrogen is supposed to make 3 bonds. So what we can do is we can add 2 fluorines to this. So now this structure is perfectly correct. So the first very basic thing is make sure you know that carbon makes 4 bonds, which element in what group makes how many bonds. That's the first thing. So moving on, let's start with the first very basic thing, and that's isomers. So let's put it over here. So what are isomers? Isomers are molecules having the same molecular formula, but they have different structure formula. What that means is that they have the same exact number of atoms, but they have a different arrangement. So one example is the one that's shown over here. So for example, you have a molecule, you've got 4 carbon atoms in a row, and this is C4H10. I mean, it has 4 carbon atoms, and you can count the hydrogens. It's got 10 hydrogen atoms. So they have 4 carbon atoms and 10 hydrogen atoms. Now, there's another way to arrange those 4 carbon atoms and 10 hydrogen atoms, and that's this one. That 3 carbon atoms could be in a line, and this 1 carbon atom could be coming out of the middle of the chain as a branch. And it's still C4H10, but it's a different molecule. It's a completely different molecule. So these two molecules are isomers of one another. And you can also check whether they are structurally correct or not. Carbon is supposed to make 4 bonds, so everywhere each of the carbon atoms is making a total of 4 bonds. This one is also making 4 bonds. So you can look at both these structures, make sure that they are correctly drawn. So both of these are making 4 bonds. So I'm just going to do a few more examples like this. So let's continue with isomers of C6H14. That's another molecule, and it's going to have several different structural formulas. So one of the isomers would be that all the 6 carbon atoms would be in a straight line. So that's 6 carbon atoms in a line and 14 hydrogens connected to them. And you can again check that all of the carbon atoms must be making 4 bonds. So you can see over here they're all making 4 bonds. Now, another way to write this is that you could have 4 carbon atoms in a row, and there could be a carbon that would be coming out of the second one. Or you could have not 4 but 5 carbon atoms in a row and a carbon coming out of the second one. That's a branch. Or you could have 5 carbon atoms in a row and there could be a carbon coming out of it from the third carbon atom. Or you could have 4 carbon atoms in a row and there could be a carbon that would be coming out of these 2 second and third carbon atoms. So that's 5 carbon atoms. Or similarly, you could have 4 carbon atoms in a row and there could be carbon chains coming out of the same carbon atom. So you could have all sorts of different arrangements on how to write those carbon atoms, how to draw those carbon atoms. They're all different molecules. They're all isomers of each other. And this is known as a condensed form. Let me just quickly highlight what a condensed form is. That you can see over here, carbon making 1 bond. So there should be 3 bonds with hydrogen. So instead of making the 3 bonds, you could just write CH3. This could be, you can condense it instead of drawing the 2 hydrogens. It's a much quicker way of doing this. You can just call this CH2. This can be called CH2 as well. This is CH2, CH2, and this is CH3. So these are known as condensed form. It's much easier or quicker to write. So for example, if I were to draw this molecule in the condensed version, this first one, carbon would have 3 hydrogens because it's making 1 bond. This one should be making 3 bonds as well. This one should be making 3 bonds with the hydrogen as well. And you've got this carbon atom, it's already making 2 bonds. So it should be making 4 bonds. So this would be CH2. And this carbon atom would be, it's making 1 bond at the moment. So this one should be CH3. So you've got, this is known as your condensed form. So remember, these are all your isomers. They're all different structures, but having the same molecular formula. We can do, when you're making isomers, you can do many different things. So you can, one thing that you could do is you can change the position of a certain group. For example, I have C4H8, and this is one of the way to write C4H8. It could be 4 carbon atoms, and there would be 8 hydrogen atoms. Each carbon atom is making 4 bonds. This one is making 4 bonds as well. I had to add a double bond because I didn't have enough hydrogen. So carbon is making 2 bonds over here and a double bond on this side. So you've got all these isomers. Now, a positional isomer is that you can change the position of the double bond. Right now, it's at the end. You can put it in the middle part over here somewhere. Or you could change the chain. You can change the arrangement of the carbon atom. So it's 1, 2, 3, and there's a carbon atom on the middle one. So all of them have the same formula. Here's another example of isomers. So I have this molecule over here. Let me highlight this. So I've got this molecule over here. This is an ethanoic acid molecule. It's CH3, C double bond O and OH. And so now you have many different ways to write this molecule. You can change the structure in many different ways. So for example, over here, I've changed the position of the double bond O is over here. The OH is over here. and each carbon atom should be making 4 bonds. So this is C2H4O2. This is another example. I have put double bonds, so it's a completely different structure. It's a correct structure, but it's again C2H4O2, but the structure is completely different compared to this one. There's an OH over here, there's an OH over here, there's a double bond in the middle. I've got this one as well, and that's also an isomer. Again, it's a double bond. The only difference between these two is that the OH were attached on different carbon atoms, but now the OH groups are attached on the same carbon atom. Here's another molecule. You've got the O is now somewhere in the middle between the two carbon atoms, so that's different from this one, but the structure is completely correct. Each carbon atom is making 4 bonds, the oxygens are making 2 bonds, the oxygen is making 2 bonds. All the hydrogens that we have over here, they're all making single bonds. Here's another isomer. So you can change the structure. The number of atoms should remain exactly the same, but you can change the structure of the molecule. So that's what an isomer is. Moving on, we'll start talking about the homologuses. I told you that all living organisms are made from organic compounds, and there are hundreds and thousands and billions of organic compounds. Even in the human body, every single molecule is composed of many different smaller molecules, and they are all different structures. So the homologuses is that since you have so many different organic compounds, that you have to classify them, just like just like the animal kingdom. Like you have so many animals that you classify them based on their properties. So the properties that you're going to base the homologuses on is that first thing is that it's a classification system for organic compounds, and it's a family of organic compounds. Like if you talk about the animal kingdom, you're going to classify them into families. Like you have reptiles, you've got mammals, so they have certain features. The same would happen with organic compounds. You have so many of them that you would classify them into families. So there are a family of organic compounds which would have similar, first thing, and you'll be asked this question very often in your exams. So they're going to have similar chemical properties, and which means that the reactions are going to be very, very similar. So and they're going to show trends in physical properties. So the physical properties are not going to be exactly identical, but they're going to show trends, and the trend in physical properties. And remember, when you talk about physical property, you're basically talking about the melting and boiling points, and the solubility, and the flammability, and the viscosity of the substance. Viscosity is the thickness. It's the thickness. It's like honey is thick. That means honey is very viscous. So water is not viscous. It flows very easily. So that's less viscous. So remember what viscosity means. So now there's a trend that's always going to be followed when you talk about physical properties, and that is that when the molecule size in a family of organic compound, it increases. If a molecule is bigger in size, it's definitely going to have a higher melting and boiling point. It's going to be more viscous. It's going to be thick. It would flow less easily. Its solubility in water would decrease, and it would also become less flammable. So they're going to show trends in physical properties. But remember this very, very important point, that if the molecule size is bigger, the melting boiling points are going to increase. They're going to evaporate less easily, and they're going to be more viscous and less soluble in water. As number 3 about the homologuses. Compounds that belong to the same family, they're going to have the same functional group. So what's a functional group? A functional group is a group of atoms or a specific structure in a molecule which is going to determine its chemical properties. So you've got a molecule. Now, pretty much all organic molecules kind of look similar. I mean, this molecule, if you look at this looks very similar to the molecules that we have drawn over here. They're kind of very, very similar. They're all carbon, a bunch of carbon and hydrogen atoms. That's known as an alkyl chain connected together. But there are some differences, and those differences are important. So there's going to be a group or structure in a molecule. For example, this molecule that we have in front of us, it's got this OH group. Now, since it's got this OH group, the OH is known as an alcohol group or a hydroxy group. So it's an alcohol group, and the molecule the rest of the chain would probably not take part in the reaction, but this part over here is the one that's the active part. You can call it the active part. You can call it the part that is the one that's involved in the reaction. So whenever this molecule would react, not the whole entire structure would react, but usually it's this part that's taking part in the reaction. And that's your functional group. That determines the function of the molecule, like with which substances would it react with. So it's a group of atoms or a specific structure in a molecule which is going to determine its chemical properties. And to quite an extent, it also determines its physical properties as well. Because apart from this difference, most structures are very similar. So this in alcohol, we can talk about other functional groups. For example, this is one functional group. If you have a carbon and carbon double bond, that's known as an alkene functional group. And you can have other functional groups as well. For example, you can spot an alcohol over again, a carbon chain with an OH group over here. And similarly, you can have, this one is a carboxylic acid functional group. It's double bond O and OH. So this group, when you have it, that's a carboxylic acid functional group. Now, so going back to homologous series, point number 4 is that molecules in the same homologous series, they're going to have the same general formula. We're going to talk about the general formulas a bit later. And the final part is that successive members differ by CH2. So this part over here would also be discussed shortly when we start studying each individual homologous series. So remember the 5 points. Let's recap. You've got similar chemical properties in a homologous series. It's a family of organic compounds having similar chemical properties. They're going to show trends in physical properties, but remember this point. They're going to have the same functional group. So it's a group of structure of atoms in the molecule that will determine the functionality of the molecule or the reactions of that molecule. And you're going to have the same general formula, and successive members differ by CH2. So we'll now be focusing on the first homologous series. We've figured out what a homologous series is. It's a family of compounds. So we're going to focus on the first homologous series, and those are your alkanes. Alkanes, the general formula is CnH2n plus 2. I'm going to come back on that general formula. Remember alkanes, they've got all bonds are going to be single bonds, and they are hydrocarbons. So the term that's used is saturated, and they're called saturated hydrocarbons. So all bonds are single bonds. Whenever something is saturated, so all bonds are going to be single bonds as shown in these molecules over here. And they're going to be hydrocarbons only containing carbon and hydrogen atoms. So you can see over here, carbons, bunch of carbons and hydrogens bonded to each other, and all bonds are single bonds. Just remember, carbon is supposed to make, it's going to make 4 bonds everywhere. So you can see carbon making 4 bonds everywhere. And whenever you draw an alkane, the general formula is CnH2n plus 2, which means N is the number of carbon atoms. So you've got N as 1. So it's going to be C1. And N would be 1 into 2 plus 2. That would give you 4. So it's CH4. If you've got N is equal to 4, that's 4 carbon atoms. So it's going to be C4. H would be 4 into 2. That's 8. 8 plus 2. That's 10. So so that's how the general formula works. Like if you don't want to draw the structure, you can just and if you know the number of carbon atoms in the molecule, you can figure out the general formula or figure out the formula of the molecule by just using the general formula, where N is the number of carbon atoms. Next one is we're going to quickly jump into naming as well. How do you name alkanes? Now, naming is that for all organic molecules, and we're only going to talk about simple organic molecules because this is O levels, iGCSE, so you don't need to know complex naming. So the simple naming is that if you have a small simple molecule, the naming is always there's a system of counting which is meth, eth, prop, but. I mean, this is how far you should know. Pent, hex, hept, oct, non, dec, that's not necessary. I mean, you should know. I mean, if you know it, that's good. What do all these words represent? These are prefixes. These are always the starting name of a molecule. Meth means 1 carbon atom. Eth means if the molecule contains 2 carbon atoms. Prop is 3. But is 4. Pent is 5, and so on. And for alkanes, the suffix or the name ends with "ane." So, for example, you have a 2 carbon atom alkane. It's a saturated alkane, a saturated molecule, hydrocarbon. The name would start with eth, and it would end with ane. So it's going to be ethane. Similarly, if you've got a molecule with 4 carbon atoms and all are single bonds, so the name 4 carbon atoms, the name would start with but and end with ane. So it's butane. So similarly, you can have pentane, you can have propane, you can have methane. So this is how alkanes are going to be named simply. Let's move on to the next thing, which is let's move on to the next homologuses, which is alkenes. So we're going to talk about what are alkenes. Alkenes are also hydrocarbons, so they only contain carbon and hydrogen atoms, but they're known as unsaturated, which means that they at least contain one carbon and carbon double bond. So not all of them are going to be single bonds. They're going to contain double bonds between the carbon atoms as well, at least one, which is why they're always referred to unsaturated. So always remember what's saturated, what's unsaturated. Saturated is all single bonds between the carbon atoms. Unsaturated is that you're going to have these double bonds between the carbon atoms. Okay, so the prefix is the same, meth, eth, etc. It's the same, the ones that we studied over here. Just remember your prefixes. Meth is 1 carbon atom, eth is 2 carbon atoms. You've got prop, but, etc. So remember your prefixes. And at the same time, you also remember the suffix for alkenes is going to be ene. It's going to be, instead of ane, it's ene. It's going to be ene. So for example, if you have a molecule and it's an alkene, it's a 2 carbon atom molecule and it has a double bond. It's a hydrocarbon, but it has a double bond in between. So the name would start with eth, it would end with ene. 3 carbon atoms, there's a double bond, it's unsaturated, it's an alkene, so the name would start with prop, which is 3 carbon atoms, and ene is the suffix. And over here, if you have a 4 carbon atom molecule, there's a double bond in between, so it's going to be but and ene. Now remember, there's going to be an additional thing over here, which is that you would have to mention the position of the double bond. What that means is the double bond could be between the first 2 carbon atoms, or the double bond could be between the second and the third carbon atom. So you're going to mention the position before the ene, which represents alkene. You're going to state which carbon atom is the double bond attached to. So if it's on the first one, it's going to be called but1-ene. If it's on the second one, it's going to be called but2-ene. So remember to always remember that the double bond position is always mentioned in the name as well. So for example, you've got 5 carbon atoms, so the name would start with pent, it would end with ene, and the double bond is at carbon number 1, so that's pent1-ene. You've got 5 carbon atoms, double bond is at position number 2, so name starts with pent, ends with ene, so the double bond position is at carbon number, it's at carbon number 2. The next one is alcohols. So here's an alcohol, CnH2n plus 1 and OH. So what's an alcohol? An alcohol is, again, you've got a carbon chain. All organic molecules have this carbon and hydrogen chain, but there's going to be an OH group present. The OH, so it's going to be known as the OH functional group. There's going to be a single bond between the O and the H. So you can have a bunch of carbon atoms, hydrogen atoms, and somewhere there's going to be an OH attached. And remember, it's the O that's going to be attached, because O forms 2 bonds. So it's going to be the O that's going to be attached to the carbon atom. So this is OH. Here's another molecule, and this has OH attached. You have a carbon and hydrogen atoms, and over here there's O and H attached, O and H attached. Remember, the O is the one that's going to be attached to the carbon atom. So this is also a molecule, and you have an OH attached. The O is the one that's going to be attached to the carbon atom. So this is what an alcohol is. So how do you name an alcohol? Again, the prefix, starting name, that's the same method, prop, but, etc. It's based on the number of carbon atoms. There's going to be an AN in the middle or an EN in the middle. That represents whether it's saturated or unsaturated. So if it's AN, that means all carbon-carbon bonds are single bonds. If it's unsaturated, then there's at least one carbon and carbon double bond somewhere. and the name is going to end with "ol", which would represent an alcohol. So for example, this molecule over here, that's 4 carbon atoms. So the name for 4 carbon atoms is bute. All of them are single bond, so that's An, and all because it's an alcohol. It's got an OH functional group. Remember to attach the O to the carbon atom. So there's an OH functional group, and it's attached to carbon number 2. You always count from the side that gives a smaller number, so you're going to count from this side. This is 1, this is 2. So the alcohol position has to be mentioned. Where is the OH attached? So you're going to write 2 over here. So in front of it. So for example, over here you've got other molecules. You've got methanol. With meth is 1 carbon atom, so that's 1 carbon atom with an OH. It's saturated, so it's An and all. You've got 3 carbon atoms, and there's an OH attached, so this is propanol, but it's propan 1-ol because the OH is attached at carbon number 1. This one over here is again 3 carbon atoms, so that's prop, saturated, so it's An, propan, nol, because it's an alcohol. There's an OH group attached, but the OH is now attached at carbon number 2. This is 1, this is 2, so it's going to be called propan 2-ol. So remember the difference between 1-ol and 2-ol. Just like alkenes, you have to mention the position of the functional group where the group is attached. This is the condensed version of this. 3 hydrogens with this, so that's CH3. There's 1 H with this, so that's CH, and there's an OH, so you put that OH in brackets, and then there's C and 3 H's, so it's CH3. So this is the condensed way of writing these molecules. The next one we're going to do is carboxylic acids. Carboxylic acids have this very, very specific, let me mark this, they have this very, very specific functional group that's attached to the molecule. So there's going to be a carbon chain, bunch of carbon and hydrogen atoms, and there's going to be this functional group that's going to be attached. It's C double bond O and OH. It has to be exactly this. Remember, everything, I mean, the structure has to be exactly this. This one is going to be called a carboxylic acid functional group. And the naming of this carboxylic acid is going to be again prefixed depending on the number of carbon atoms. So it's going to be meth, eth, prop, and bute, and so on, depending on the number of carbon atoms. An, or they could be En over here as well, depending whether it's saturated or unsaturated, and the name would end with oic acid. So for example, if you have a 2 carbon atom carboxylic acid, 2 carbon atoms, there's a double bond O and OH attached, so that's the carboxylic acid functional group. The rest is hydrogen atoms, so 3 hydrogen atoms with this. So this one has 2 carbon atoms, so it's eth, anoic acid, because all are single bonds, so it's An and oic acid. If you've got 4 carbon atoms, so 4 carbon atoms, you have a carboxylic acid functional group. Again, I'm highlighting that this is the carboxylic acid functional group. So it's going to be 4 carbon atoms. That's bute, denoic acid, because it's a carboxylic acid. Similarly, you've got 3 carbon atoms. So if it's 3 carbon atoms, then it's 3 carbon atoms is prop, and it would be called propanoic acid. And we can also talk about the general formula. The general formula that I gave you for this is CnH2n plus 1 COOH. So if you don't want to draw the structure and you want to directly know the formula of the carboxylic acid, you can use the general formula. The problem with the general formula is you have to remember that the general formula, let's focus on this, and let me highlight this. If you use the general formula, remember N in this case is, and let me highlight this, what's the value of N? N is the number of carbon atoms minus 1. It's 1 less than the number of carbon atoms. So if you're talking about butanoic acid, it's 4 carbon atoms. N would be taken as 3. So remember, so this is one hack that you have to do, that the value of N in the formula, in the general formula, if you don't want to draw the structure, you just want to know the formula of the molecule directly, just remember that N is 1 less than the number of carbon atoms. So if So in this case, butanoic acid, N is 4. Sorry, the number of carbon atoms is 4. You're going to take N is equal to 3. So it's going to be C3. H would become 3 into 2, that's 6. X plus 1, that's 7. So it's going to be C3H7 and COOH, which is exactly the same. This is C3H7. I mean, you add them up. So this would give you C3. And H is going to be 7. And the rest is CO and OH. So C3H7, COOH. Same with propanoic acid. You've got 3 carbon atoms. You're going to take N as 1 less than the number of carbon atoms. So that's, if you've got 3 carbon atoms, N would be taken as 2. So it's going to be C2. H would be 2 into 2, 4. 4 plus 1, that's 5. C2H5 and COOH. So this is exactly what you have. You've got C2H5 over here, and you've got COOH. So you can directly figure out the formula of the carboxylic acid by using the general formula, but remember N, the number of carbon atoms minus 1, that's the value of N. And also remember that the functional group could be on the right side, it could also be on the left side, but if it's on the left side, make sure you draw it exactly. I mean, the connectivity should be exactly the same. It's going to be C double bond O and OH. And remember, the O is the one that's going to be connected. So C double bond O and OH, if it's on this side, C double bond O and OH. So that's our molecules. So why don't we just do a small exercise? Let's start with the first one. Okay, let's try and draw each one of these molecules. So I'm going to start off with ethane. So now that's an alkane. What is the meaning of it? That means I've got 2 carbon atoms. So I've got 2 carbon atoms, and it's an alkane. So that means it's a saturated molecule. So you can add the hydrogens now. An alkane is a hydrocarbon, so this one should have 3 hydrogens. So I'm just going to go with condensed formulas. And this one is also going to have 3 hydrogens, so that carbon is able to make 4 bonds. Let's try the other one. That's pent-1-ene. So what is pent? Pent is 5. So you've got 5 carbon atoms, right? And it's an alkene, it's an ene, so that means there's a double bond at position number 1. So we're going to put a double bond at position number 1, and I'm going to add in the hydrogens. So this one will have 3 hydrogens. This carbon right now is making 2 bonds, so there should be 2 hydrogens attached with this. This carbon atom was also making 2 bonds, so there should be 2 hydrogens attached to this. This one should have 1 hydrogen. This one should have 2 hydrogens. So I'm just drawing them in a displayed way so that you can see the double bond. So this is pent-1-ene. Then they've got butan-2-ol. So bute is what? Bute is 4 carbon atoms. So that's 1, 2, 3, and 4 carbon atoms. So that's bute. And it's an alcohol. So it's got an OH. So this is an ol, and it's got an OH at position number 2. So why don't you put an OH at position number 2 and add in the hydrogen? So there would be 3 hydrogens with this one. This carbon is making 2 bonds, so there should be 2 hydrogens with this. This carbon atom over here is already making 3 bonds, so there's only space for 1 more hydrogen. And this carbon atom is going to be making bonds with 3 hydrogens. This is butan-2-ol. Next one is methanoic acid. So meth is 1 carbon atom. So meth is a molecule with 1 carbon atom. It's a carboxylic acid. Carboxylic acids, all of them, they have C double bond O and OH groups. And you can complete the bonds carbon is making. At the moment, it's making 3 bonds. So there should be 4 bonds with this. So I'm going to add in an H with this. Next one, I've got propan-2-ol. Propan-2-ol is going to be, again, it's an alcohol. So prop is 3 carbon atoms, and it's an alcohol, so there's an OH at position number 2. So on the second carbon atom, add an OH. And you can add in the hydrogens. So there would be 3 hydrogens with this. three bonds already, so they're going to be just one hydrogen. This one is going to have three hydrogens attached to it. You've got ethene. Now ethene is eth is two carbon atoms. It's an alkene, so that means ene. So that means there's a double bond, and you can add in the hydrogens, two hydrogens with this, so you can. So that I can draw the hydrogens instead of writing a condensed form. So this is what ethene would look like. And the last one is pentanoic acid. So pent is a total of 5 carbon atoms. So that's 5. It's a carboxylic acid. So there's going to be double bond O. And there's going to be OH. This one will have 2 hydrogens. This one will have 2 hydrogens. This one will also have. And this one over here will have 3 hydrogens attached to it. So we're now going to focus on fractional distillation of crude oil. We're going to focus on crude oil. What is crude oil? We're done with naming. We haven't done the naming of esters yet. That would be done when we study esters. So let's focus on what crude oil is. So just a few images. This is what crude oil is. It's a black tar-like substance that you obtain from the Earth's crust. This is how you dig for oil under the layers under very high compression. The fossils and the bones and the animals and the dead vegetable, everything, all living organisms, they get compressed and they turn into oil. So that's where you get most of your organic compounds. For the petrochemical industry, they're very good for combustion. They're a good source of energy, and the world has been using crude oil for the last, at least excessively for the last 100 or 200 years, for specifically energy. Now, crude oil, remember, is a mixture. It's a mixture of many different things. It's a mixture that contains petroleum gases. You've got naphtha, you've got gasoline, that's the fuel that you add in your cars. You've got kerosene, airplanes run on that, diesel that's used in heavy transportation. So it's a mixture of many different compounds. You've got fuel oil or furnace oil that's used for power generation. Then you've got lubricating fractions. You use oil for lubrication. You use it as grease, as petroleum jelly, and then you have residue, that's bitumen, that's used for making roads. So crude oil is a mixture of many different compounds, and you should know what those compounds are. Now, crude oil is separated into its different fractions. Separation happens because each of the compounds they have differences in boiling point. So what you do is you take a furnace and you heat the oil. This oil over here, it is vaporized. It's heated at two very high temperatures, and usually it's in excess of 400 degrees centigrade. It vaporizes, and all the petroleum, also known as crude oil, it vaporizes, and then you pass it through this fractionating column, which is like a chimney. The vapor rises up as because it's hot vapor. It's vaporized crude oil that rises up this chimney. And so at the bottom, they're very high temperatures. But at the top, the temperature kind of starts decreasing. As the vapor continues to rise, the temperature starts to decrease, and you have lower temperatures at the top. Now, when the vapor starts to rise, then different molecules, they start to condense because the temperature constantly drops. So you're going to have very high temperatures at the bottom, and you're going to have kind of low temperatures. I mean, this at the top would be close to room temperature. So you have very low temperatures at the top. So substances that have higher melting, and this is written over here. So you've got big molecules which have high melting and boiling points. They condense very quickly. So if something has very high melting and boiling points, it would condense. If the temperature drops, it's going to condense very quickly. So big molecules, they condense early. So you've got different trays inside this fractionating column, and molecules, they start to condense. So I can show you. So there would be some molecules, big molecules, that would condense very early. Smaller molecules would continue to rise. Their melting and boiling points are much lower, so they're going to condense at the top. Small molecules, they have low melting and boiling points, so they don't condense easily. because the temperature has to be really, you have to really decrease the temperature for them to condense, because the boiling points are really low. So so at the top, always remember, at the top of these trays, you're going to get small molecules, and the bottom, the molecules that are going to condense are going to be your big molecules. And remember, I told you about the properties of these molecules, that if you have a big molecule, then its melting and boiling points are definitely higher, and they are more viscous, and they are less flammable as well. They don't burn easily. So waxes, bitumen that's used for making roads, all of these things, they don't burn easily. They're very viscous, they're very thick, and they've got very high melting and boiling points. Substances higher up in the trays, you get smaller molecules. At lower temperatures, you get smaller molecules, they condense. These smaller molecules are going to be they would flow more easily. They would have very low melting and boiling points, so they're going to be volatile liquids. For example, gasoline is very volatile, it evaporates very quickly. Petroleum gases are already gases. I mean, they don't condense at all, and they flow very easily, and they burn very, very efficiently. So small molecules, they burn very easily. So this is what's happening. The temperature continues to drop as you move upwards. So remember the order. What's important is remember the order of these substances that you're going to get in these trays. Big molecules, residues at the bottom, lubricating fractions, fuel oil at the bottom. These are big molecules. And at the top, you're going to get smaller and smaller molecules. They're going to condense naphtha, gasoline, etc., kerosene, diesel. So you have to remember the order in which these molecules are going to condense. And you have to remember the uses as well. Which substance gets used for what? Residue, bitumen, that's for making roads. I'm going to repeat the uses. Lubricating fractions, that's waxes. Petroleum jellies, that's used for car waxes, for general lubrication. You've got fuel oil, furnace oil, that's for power generation. Diesel, that's for heavy transportation, ships, trucks, etc. They use diesel. Kerosene, that's used for airplanes. It's airplane fuel. It's also known as paraffin. In older times, lamps were actually, you had a lot of paraffin lamps, but that's now obsolete. No one uses paraffin lamps anymore. Gasoline, that's cars. Naphtha, that's used as basic. Remember, I told you the medicine industry, that's also organic, because all living organisms are made from carbon compounds, so they're also organic. So medicine, most of the medicine that you eat or have or inject in your bloodstream, that's most of it is the organic molecules, and you obtain them from naphtha. They're used as a basic building block for the chemical industry. So you want to build a molecule, you use naphtha for that. It's a feedstock for the chemical industry. And then you've got petroleum gases, which such as methane. That so your stoves, your heaters, your heating systems, they run on petroleum gases. Domestic heating, cooking, etc. So they are used there. So remember fractional distillation of crude oil and the separation of these compounds in crude oil. This is a mixture of many different compounds. Separation happens because the mixture has many different compounds with different boiling points. Now, so that's all about crude oil. So let's now move to the first homologous season. Now we're going to study the reactions of these homologuses. So we're going to start off with alkanes, and we've previously studied naming alkanes. So what were alkanes? Alkanes were your saturated hydrocarbons. Saturated meaning that they were hydrocarbons that had all single bonds, carbon and carbon bonds. All of them were single bonds. So, and let me highlight this. So these were all alkanes. You can draw a displayed formula or a structural formula, a more condensed version of it, where you don't show the bonds, all of the bonds. So there's this one is a 4-carbon atom alkane, all single bonds. So I can draw another one. Let's draw a 3-carbon atom alkane. So this carbon atom at the end would have 3 hydrogens. So you can write it as CH3. This carbon atom over here would have 2 hydrogens. You can write it as CH2. This carbon atom has 3 hydrogens, and you can write it as CH3. So this is CH3, CH2, CH3. This one is propane. It's got 3 carbon atoms, so you call it propane. Now the first thing about alkanes is, let's talk about the physical properties. So the physical properties are that they have usually low melting and boiling points. Alkanes don't have really high melting and boiling points, and they're not soluble in water. So it's very hard to dissolve an alkane, and no electric conduction. They're neutral compounds. They're not acidic nor basic. And also remember about properties that as the size of the molecule increases, so remember this about properties of organic compounds, that as the size increases, the melting and boiling point and viscosity would increase, and the flammability of the molecule would decrease. So they're going to become solids if it's a big molecule. So if there's an alkane that has 50 carbon atoms, then it's probably a solid. It's going to be very viscous, it's going to be thick, it's going to be wax-like, and it's going to be very less flammable. So it's very hard to actually burn waxes. So the flammability starts to decrease. Now, the first thing about reactions of alkanes is that, and let me set this. So the first thing about reactions of alkanes is that they are not very reactive. You don't have a lot of reactions except for a few, one of which is substitution, also known as chlorination or bromination. What happens in this reaction is that, so what happens in this reaction is, and let me, okay, fine. So what happens in this reaction is that you take an alkane, for example, the propane that we drew earlier, you take that alkane, you react it with Cl2, and remember the conditions are that it's a photochemical reaction and ultraviolet light is a must. It has to be there. So you need to add, you need to have sunlight. That's basically sunlight. Because without the sunlight, the Cl-Cl bond would not break. The Cl2 molecule, the Cl atoms are bonded together. Now what happens in this reaction is that one of the H, so it could be any H, it could be this H, it could be this H, any of the hydrogens, they would break off. They would combine with Cl to form HCl. So an HCl molecule is going to be, it's going to be formed. And what happens is that the other Cl then takes its place. So one of the H gets knocked out. In this case, it's the middle H over here that's getting knocked out, and it's being substituted by Cl, which is why it's called a substitution reaction. So any H could be substituted, and more than one H could also be substituted. So I can have, I mean, if we have this reaction, what we can also have that more than one H could be substituted. So you could have an alkane, and these are the hydrogens. So any number of hydrogens can be substituted by Cl. So I can have the H over here, and over here, and over here. All of them, they can be substituted by Cl. So you would have to increase the number of Cl2 molecules if you want more H to be substituted. And all the H that are substituted, for example, in this case, there are 4 H substituted, so they're going to form 4 HCl molecules. So this is what's happening. Cl goes, combines with any of the H, or any or all of them, so it can substitute all of them, or just one of them. It depends how much Cl2 are you adding. So if you're adding too much Cl2, then all of the H would eventually, they're going to get substituted by Cl. And all of them are going to get substituted, and all the H atoms that get lost, they're going to form bonds with Cl as well, and they're going to form HCl. So HCl is always produced. So that's our substitution reaction. Remember this reaction, it's a very important reaction. And it's a very random reaction because you're not sure how many Cls are going to substitute the H atoms. So it could be 1 Cl, it could be 4 Cl as I've shown over here, or it could be all the 8 hydrogens could be substituted by Cl. So it depends depending on how much Cl2 you're adding to the reaction. The next one is obviously combustion reactions, and all organic molecules that undergo combustion. So this reaction, we're not going to study this later as well, because just remember that any organic molecule, it's going to undergo combustion. It's going to burn with oxygen to produce carbon dioxide and a water molecule, and this applies to all reactions. So I can think of an alcohol like ethanol, C2H5OH, and that would also react with oxygen to produce the same thing, which is carbon dioxide and H2O always. So they're all going to burn, and you can balance it accordingly. So there's going to be 2 carbon dioxides, there are 6 hydrogens on the other side, so there would be 3 water molecules, and there are 4 oxygens and 3 oxygens over here. So that's a total of 7 oxygens. So 1 over here, so there should be 6 oxygens over here. So that's combustion. So it would be applied to any, whether it's you can apply it to ethanoic acid as well. So CH3COOH. You can burn it, and it would produce the same thing. It would produce carbon dioxide and H2O. And so you've got two carbon dioxide molecules, and you've got the four hydrogens on the left side. So there should be two water molecules, and you can balance the oxygen. So that's 4 plus 2, that's 6. You got two already over here, so you need 4 oxygen. So there would be 2 oxygen molecules. So this is your combustion reaction. Any hydrocarbon, alkane, organic compound would undergo a combustion reaction. But then you're going to have incomplete combustion as well. Now, the only difference in incomplete combustion is that there's a limited supply of oxygen, so they're not going to burn completely. So in addition to CO2 might be produced, but carbon monoxide can also be produced, and carbon, which is soot, the black substance, that could also be produced in the combustion reaction. So carbon monoxide, remember, is a toxic, poisonous gas which causes choking. So if you have an alkane like C2H5 ethane, and if it undergoes incomplete combustion, so it would produce carbon monoxide, it could produce carbon as well, and I mean, we can keep carbon dioxide. So in addition to carbon dioxide, it could also produce these compounds. So this is not a balanced equation, but just remember that in addition to carbon dioxide, carbon monoxide and carbon can also be produced if there's a limited supply of oxygen and it's an incomplete reaction. The next thing that we're going to talk about is the cracking of oil. So we're pretty much kind of done with alkanes. Cracking of oil is basically, we can think of it as part of alkanes. You've got big molecules. You've got long chain hydrocarbons, and long chain means that we can have very, very big molecules. We can have molecules that could have hundreds of carbon atoms. So if you have a long chain hydrocarbon, they're not very useful. Why are they not very useful? Because they've got high melting and boiling points. So they're solids. Like wax is a solid. Now, solids can't move, they can't flow, so you can't use them as fuels because they're not going to flow through pipes. So very difficult for them. Like, you can't use wax as a fuel for your stove. Why? Because wax would be stuck in the pipes. It's not going to move. So it would be very hard to actually handle wax. And they're not going to be very flammable. So wax burns very, very slowly, not very good as a source of energy, and they're very viscous, which obviously means the same thing, that they don't flow very easily. So what you do is, under these conditions at high temperatures, and which is greater than 450 centigrade, plus you add a catalyst, you add zeolites or Al2O3, which is or SiO2 as well. These are used as catalyst. The big molecules are broken down into smaller, more useful chains. So the smaller ones, so if you break a big molecule into a smaller molecule, the advantage is that the smaller molecules, they've got lower melting and boiling points. So there would be gases, or they're going to be volatile liquids like petrol or gasoline. They would flow very easily. They burn very efficiently. They're very flammable, and they're not viscous. They don't get stuck in the pipes. They're going to flow very, very smoothly. So the gas that comes in your stoves, that travels very quickly. I mean, you can transport it through pipes. The fuel that's in your car, that travels very easily because so you can have an injection system. The solvent or the liquid would flow through those pipes. So they're not very viscous as well. So you want the big molecule to be broken down into smaller molecules. So what happens in cracking is, let's say you have a big molecule like a 60 carbon atom alkane. This is an alkane. How do I know it's an alkane? It's this one is CN, and it's H2N plus 2, right? So I mean, the formula of the molecule, it fits the general formula. So if I have a big alkane, a big molecule, I'm going to break it down into smaller alkenes, and so I mean, this is where it's written. The molecule would be broken down into 3 things. It could be broken down, and it's a random process. It could break down into any number of molecules. It could be so it would be broken down into smaller alkanes. Remember the general formula of alkanes, that's CnH2n plus 2. It would be broken down into alkenes as well, that's CnH2n, or it might give off hydrogen gas. So I've done a few examples. So for example, over here, I've broken this molecule down into these 4 compounds. I had an alkene, which is C10H20. I had an alkane, according to the general formula, that's C15H32. Then I had another, so this one, and then I had another alkene, which is C15H30, and then another molecule was produced, which was C20H40. Now, the thing is that if I add up all the molecules, the number of carbon atoms and the number of hydrogen atoms must add up to this thing. So that's one way of breaking, and it's a completely random process. What you just need to know is that whatever molecule that whatever formula that you write, it must fit the general formula of an alkane or alkene or hydrogen gas. So here's another cracking reaction. This is being broken down into a molecule that contains 20 carbon atoms, and one contains 40 carbon atoms. So that gives you a total of 60 carbon atoms. So this one is an alkene, CnH2n, so that's C20H40. And this one is also an alkene, so that's C40 and H80. So if you add them up, you would be short of hydrogen, so you add the hydrogen gas, that would also be produced. So you can break the alkane into any number of ways. Here's another way of breaking the alkane. You got a molecule with 15 carbon atoms, your molecule which had 45 carbon atoms. That gives you a total of 60 carbon atoms. I turned this into an alkane, so it's CnH2n plus 2, so that's 2n is 30, 30 plus 2 is 32. This is an alkene, so it's CnH2n, 45, and this would be 90. You add them up, and this gives you exactly H being 122. So remember what cracking is when you're doing cracking. The alkane can be broken down into, the rule is they're just going to be broken down into smaller molecules. You can't really predict what the smaller molecules is. So you'll get hundreds of different types of smaller molecules. The only thing is that if you were to write an equation, then the molecule would be broken down into, you can write any random molecule, except that it should be an alkane or an alkene or hydrogen gas or all three. And the total number of atoms must add up to the atoms that are present in this original molecule. So they're going to add up to this original molecule over here. Now we're going to move towards our next homologuses, and we're going to study their reactions and physical properties. We're going to talk about alkenes. The general formula for an alkene is CnH2n. So they're basically unsaturated hydrocarbons, which means that they are hydrocarbons, which means that they only contain carbon and hydrogen atoms. And there's going to be at least one double bond somewhere. So for example, if I make an alkene, a 3-carbon atom alkene, so there's got to be a double bond somewhere between the carbon atoms, and you can then, let me redo this. So if I make a 3-carbon atom alkene, so there's going to be a double bond somewhere between the 2 carbon atoms, and I can add up the hydrogens to make 4 bonds for carbon. So this would be CH, this would be CH3, because it requires 3 hydrogens to complete its bonds. So this one is an alkene. This the molecule name is prop because it's got 3 carbon atoms, and it's going to be followed by ene. So this is your propene. Now the physical properties of alkanes are kind of the same as the physical properties of alkenes are the same as the physical properties of alkanes. Very similar. They've got low melting and boiling points, and they're not soluble in water, and there's no electric conduction. They're neutral compounds. And also remember, as the size of the molecule increases, the melting, boiling points and the viscosity would increase as well, and the flammability would decrease. It would become much harder to burn the substance if the molecule is bigger in size. So what type of reactions do alkenes undergo? Now, all alkenes, they undergo this type of reaction. They're known as addition reactions. Most of the reactions for alkenes are known as addition reactions. What happens in an addition reaction is that you have an alkene. For example, over here you have butene. It's 4 carbon atoms, and there's double bond at the first carbon atom from the right. So this is butene. And what's going to happen is that you're going to react it with a particular molecule. Let's call that molecule XY. What's going to happen is that the double bond between the 2 carbon atoms, the reaction is going to happen only with these 2 carbon atoms, not these two. So the reaction would only be with the double bond. So the 2 carbon atoms, the double bond between them is going to go away, and the X and the Y are going to get added to those 2 carbon atoms that were previously making double bonds. So the double bond turns into a single bond. So double bond over here, it would turn into a single bond, and X and Y are going to react with it. So I'm going to show you some examples for this. So for example, I've got a molecule I'll do a complicated molecule. Let's say I have this molecule. This will have 3 hydrogens. This one over here will have one hydrogen. This one will have one hydrogen as well, and this one will also have one hydrogen. So if I uh, and let's so if I react it with XY, what would happen is that everything would remain exactly the same, apart from the fact. So I'm going to do the changes over here. So if I reacted with this molecule, so everything remains exactly the same, except for the fact that the double bond between the two carbon atoms would turn into a single bond. So I'm going to replace it with a single bond. And remember, the reaction would happen with these two carbon atoms, the one that were making double bonds. An X would get attached over here, and a Y would get attached over here. So it's going to be called an addition reactions. Things are getting added to it. So there are multiple different types of addition reactions, and the first one that we're going to do is known as a bromination reaction. So in a bromination reaction, the molecule is Br2. Whenever you see a double bond, the double bond is going to go away. And in its place, the two carbon atoms, the bromines, will get attached to it. So that's what your addition reaction is. The conditions for a bromination reaction is that you need aqueous or bromine, which is aqueous, or in CCl4 solvent, that's an inert solvent. So the solvent is going to be water or this inert solvent, and there's got to be absence of light, and this reaction happens at room temperature and pressure. So RTP stands for room temperature and pressure. So here's another example. You've got an alkene. There's a double bond over here, and the double bond is going to turn into a single bond. So that's our single bond now. And the two carbon atoms, the bromine is going to get added to the carbons which were making double bonds. So they're going to get added to these two carbon atoms, one on this and one on the other one. The importance of a bromination reaction, it's a very, very important reaction. It's used as a test for identifying alkenes or unsaturated molecules, or molecules that have these double bonds. How can you identify that? Because bromine has a red-brown color. It's reddish-brown in color, and when it reacts, it gets used up and the color disappears. So the red-brown Br2 is decolorized. So that's an indication that you have an alkene. So you take a beaker that has alkenes and you put a few drops of bromine in it, and the red-brown color of bromine is going to vanish. So that means the molecule is unsaturated, that it has these double bonds in it. So that's the first reaction. That's known as a bromination reaction. The next one is known as a hydration reaction of alkenes. Same reaction, but this time you're reacting it with a water molecule. So you have an alkene, you have a double bond between the carbon atoms. Same thing happens. The double bond over here would turn into a single bond. So double bond, it turns into a single bond. And things get added to those two carbon atoms that were previously making double bonds. So there's going to be an H added, and there's going to be an OH added. So water would split up, an H would get added, and an OH would get added, and it would turn into an alcohol. So alcohols are formed in a hydration reaction. The conditions for this reaction, they have to be memorized. Remember, hydration happens at 300 degrees centigrade, and you need an acid catalyst for that. And the conditions, so an acid catalyst like phosphoric acid, and the pressure needs to be 60 atmospheres. So you need high pressure for that as well. So this is what a hydration reaction looks like. The next one, the only purpose of this reaction is to form alcohols. Now the next reaction is called a hydrogenation reaction. So hydrogenation is a reaction with H2. Same reaction. You have an alkene, you have an unsaturated molecule. You've got an alkene, a double bond between the carbon atoms, and exactly the same thing would happen. That the double bond would turn into a single bond, and this time H atoms. When hydrogenation happens, H2 molecule, the H atoms, they are the ones that get added to these two carbon atoms, and the molecule becomes saturated. It turns into an alkane. So an alkene turns into an alkane. An unsaturated molecule, it turns into an alkane. Now, the importance of this reaction is that it's a very important industrial reaction, and that's the manufacture of margarine. Why? Because an unsaturated vegetable oil molecule, I mean, you know what vegetable oil is. It is liquid in, you use it for frying eggs, for example, and it's liquid and it has low melting points. It's unsaturated, which means that it has a lot of double bonds. So what I can do is I can I'm going to show you an unsaturated vegetable oil molecule. So here you go. You've got an unsaturated fat or vegetable oil molecule. You can see that the molecule is a complicated molecule. It's a big molecule, but it's got these double bonds in it. It's an unsaturated molecule. The carbon chain doesn't have single bonds. There are double bonds at different positions. So when you hydrogenate it, when you add hydrogen, the double bonds they vanish and H atoms get added to it. So the molecule turns from an unsaturated molecule, the carbon having double bonds, it turns into carbon having single bonds only. So what's the purpose of this reaction? The purpose of this reaction is that if you add hydrogens, just a few of them, if you add hydrogens, you get rid of the double bonds, the size of the molecule becomes bigger. This molecule is slightly bigger compared to this molecule. And if the size increases, that indicates that whenever size increases, that indicates that the melting and boiling points are going to be higher. So, so unsaturated vegetable oil, which has low melting points, it's a liquid in nature. It's a slightly smaller molecule. When hydrogen gets added, it turns into a saturated molecule. It's now a slightly bigger molecule. So this is what margarine is. Margarine is like butter. It's a solid, so you can use it for different purposes. Like you can put it on bread. You can't use vegetable oil on bread. Remember, both are almost the same thing, except that you turned a molecule of vegetable oil, you added hydrogens to it, and it became a bigger molecule. And when it became a bigger molecule, the melting and boiling points increase. Remember, the trend is always that if you have a bigger molecule, the melting and boiling points are going to be higher as the size increases and you have a higher melting point. Okay, exactly the way it's shown over here. Adding hydrogens to this molecule will increase the size of the molecule. So it turns into a solid substance or a semi-solid substance. So that's how margarine is manufactured industrially. The next thing, what we're going to do is we're going to try and do these reactions. We did bromination, we did hydrogenation, and we did hydration reactions. So I'm going to pick the first one, pentoene, and I'm going to do all of that to that molecule. So let's do it over here. Pent-2-ene means you've got 5 carbon atoms. So that's my pent, 5 carbon atoms. 2-ene means that the double bond is on the second carbon atom. So I've put my double bond over there and I can add the hydrogens. There would be 3 hydrogens with this. There are going to be 2 hydrogens with this one. There's going to be 1H with this one. There's going to be 1H with this one. And there are going to be 3 hydrogens with this. So I'm going to do all my working on this. I'm going to draw or copy 3 of these molecules. So this is one. Here's another one. And here's my third one. First one, I'm going to brominate it. I'm going to add bromine at room temperature, bromine aqueous, CCl4 room temperature, absence of light. What would happen is that the double bond between them is going to vanish and that double bond would turn into a single bond. And bromines are going to get added to the 2 carbon atoms. Remember, it's only the double bond that's going to react, so only this place. So that's my bromination reaction. Next one, I'm going to try and hydrate it. So I'm going to hydrate this one. Water, I'm going to add water to it. And the conditions are 60 atmospheres, 300 degrees centigrade temperature, and you've got a phosphoric acid catalyst. So the double bond is going to vanish as well. And when it goes away, it's going to turn into a single bond. And in hydration, you got an H and an OH that are going to get added to that position. The third one, I'm going to do hydrogenation. Same thing. That's for manufacture of margarine. That's hydrogen plus nickel catalyst, 200 degrees centigrade. The double bond is going to go away, and the double bond will turn into a single bond. And hydrogens are going to get added to these 2 carbon atoms. So I've drawn the results of hydrating pent-2-ene, of hydrogenation of pent-2-ene, and also bromination of pent-2-ene. So that's what's going to happen. Let's do the other one as well. There was another example. Let's try and copy this one. So I'm going to brominate it. I'm going to do 3 reactions. So I'm going to copy this and let's put it somewhere else. So I'm going to make 3 copies of this. So that's one of the molecule. Just 1 second. So I'm going to make 3 copies of this. That's one. Here's the second one. And here's the third one. So starting with the first one over here, let's brominate it. Let's do bromination. Let's add bromine aqueous to this molecule. And when we add bromine aqueous, both double bonds are going to go away. This one is going to go away. This one is going to go away. They're going to be replaced with single bonds. So they're going to be replaced with single bonds. And these 2 carbon atoms, bromines, are going to get added to these 2 carbon atoms. And the same over here, bromines are going to get added to these 2 carbon atoms as well. So both double bonds are going to take part in the reaction. Similarly, this one, I'm going to hydrate this molecule. I'm going to add water to it at 300 degrees centigrade, phosphoric acid catalyst, and 60 atmospheric pressure. The same thing would happen. The double bond is going to go away. So get rid of those, both of those double bonds, replace them with single bonds. And what would happen? H and OH will get added over here. So a water molecule gets added over here. And an H and an OH will get added over here as well. So that's the result of a hydration reaction. Let's do the third one. I'm going to hydrogenate it, add nickel with H2 catalyst. Double bonds are going to go away. They're going to be replaced by single bonds. And H atoms are going to get added here, as well as H atoms will get added over here as well. So that's what our hydrogenation reaction is. So I've done examples. So remember, just a quick recap. The quick recap is you've got a bromination reaction. The importance of the bromination reaction, it's a test for identifying unsaturated molecules or alkenes. The red-brown bromine will decolorize, so that's the test. The next one is hydration. You add water to it, it forms an alcohol. The next one is hydrogenation. You add H2 and the molecule size becomes bigger. So you specifically use it to make or form margarine because it's a bigger molecule compared to an unsaturated vegetable oil molecule. So the melting and boiling points are higher and it is therefore a solid. Let's move on and let's discuss also what polymerization also is. So we're now going to move towards addition polymerizations. We did all the reactions for alkenes. Now we're going to talk about addition polymerization, which is I'm going to first explain what a polymer is. Polymer is a large macromolecule. It's a big molecule. It's a huge molecule when many small monomers join together. So think of these boxes as being your monomers, and if you connect them together, so these are small individual molecules, this one, so they're all individual molecules. And if I join them together by a chemical bond, they're all going to link up. They would bond with each other. And if thousands of them, they link up, then it would be a huge chain of monomers all linked up together, and that would be known as your macromolecule. That is going to be called your polymer. So it's a macromolecule, big molecule, and in addition, polymers, these boxes, these small molecules, these are known as your monomers. These monomers simply means a single unit. So these monomers are your unsaturated molecules or alkenes. What's an unsaturated molecule? That's basically an alkene. Anything that has a double bond, we just did that. For example, all of them, these are alkenes. If you see a double bond, that's an unsaturated molecule. So the monomer or the small individual molecules that are going to link up, these are your alkenes. So we're going to start with the first one. The first addition polymer is going to be, we're going to make polyethylene. And polyethylene is, the word ethene over here is my monomer. Polyethylene is a substance that's your normal plastic bags that you carry items in. Those are usually referred to as polyethylene. So ethene is the monomer. So ethene molecule, it has just 2 carbon atoms, and it's got these double bonds between the two carbon atoms, so that makes it an alkene, which means that it's unsaturated. Uh, so I can add another, and remember there would be hundreds of thousands of these monomers. So I'm drawing the fourth one. So there's carbon makes 4 bonds, so there's going to be 1H and 1H. Now, one thing that you should do is when you're making these monomers, do one thing, and that is around the double bond, make sure you don't draw anything on the right side or on the left side of the double bond. So if you want to make a bond connecting this carbon atom, make it above or below, not to the left or to the right. So for example, this H over here, what I'm going to do with this H is I'm going to pick this up and I'm going to take it above and turn it around so that the H is bonded not on the right side or the left side, it's on top. So make sure the right side and the left side, they're all they're not, there's nothing there. So what happens, how is a polymer formed? And let me do this again. The way the polymer is formed is that originally you had these double bonds. So there were double bonds in between all these carbon atoms. And what's going to happen is that the double bonds are going to break. It's the double bonded carbon atoms, the one that I've highlighted over here. It's the double bonded carbon atoms, the one that you see over here. They're the ones that are going to link up. So you've got a double bond, you've got a double bond, you've got a double bond, and the double bonds would all break and they would turn into single bonds. So you remove this double bond and I'm going to turn it into a single bond. So I've removed that. And the carbon atoms are now short of one bond, so they're going to link up with each other. So they're all of them are going to link up with each other. So there would be thousands of such monomers, and they would all be joining up. This was an H over here. So they would all be joining up. And that's how your polymer is formed. And this is referred to, remember to draw a continuation bond. This just shows that there are other monomers that are still linking up. So the molecule has not ended over here. It's not just 3 monomers, it's hundreds of thousands of monomers that have linked up, forming a very, very long chain. This is the repeat unit. This is the thing that's repeating over and over again. It's continuously repeating. So in the chain, this thing would be repeating over and over again. So there's another way to represent this polymer, and that is that what you can do is you can make only this section, and you can draw a continuation bond over here, which shows that this repeat unit is again repeating over and over again, and you can put brackets over it, and n is the number of times it's going to repeat. So if there are thousands of them, so n would be equal to 1,000. So 1,000 times this thing would repeat. If they are repeating for 100 times, so that's a smaller chain. It could be 50,000 times. That could be a very, very long chain. So that's what a polymer is. It's like this long strand of monomers all linked up together. So let's try and do another one. And I'm going to draw polypropene just for. I'm going to do it over here just to show you how polypropene is going to be formed. Polypropene, the monomer is propene. So propene is prop. It's got these 3 carbon atoms, and it has, you can add the H atoms. Each carbon atom should be making 4 bonds. So I'm adding the H atoms, and this carbon will have 3 hydrogens with it. So writing it in the condensed notation. So what we can do is, first thing is redraw this. I told you, you see the double bond? Those are the carbon atoms that are going to link up with other monomers. So you see a double bond. Nothing should be drawn on the right side or on the left side of this double bond. So I've drawn an H over here. So what I can do is I can, instead of drawing this H to the right, I can bend it downwards, right? So I'm drawing it below. Similarly, the CH3, I'm going to push it down. I'm going to keep this side empty. So that's what you're going to do. So not breaking the bond. I'm just changing the direction of the bond. So remember, I'm not changing the molecule. I'm just sort of twisting it around. So the CH3, so that this side is empty, this side is empty. So that's my monomer. And there would be hundreds of these monomers. So I'm just going to draw, let's say I'm going to draw 4 of them. So here are my 4 monomers. And remember the double bond carbon atoms that I put them in a box. These are the ones that are going to react. So I'm going to just remove the. Let me get rid of the box. That was just to highlight that it's these carbon atoms. And then the double bond would break. It would turn into a single bond. So I'm going to rub all of the double bonds, turn them into single bonds. And it's these carbon atoms that are now short of bonds. So they're going to link up. This one would link up with this carbon atom. This one would link up. I mean, they're all trying to make the 4th bond. So they're going to link up. They're going to link up. They're going to link up. And that's my polypropene. I started off with a propene, and this is my polypropene. And what's the repeat unit that's repeating over and over again in this really long strand, a really long thread? That's this thing. So what we can do is I'm just going to copy this. I mean, the short notation for this would be I'm just going to copy this. So I think that's copied. I'm going to paste it here. And so this thing is repeating over and over again. And I'm just going to put a bracket and write N next to it. So that's my addition polymer. So this is exactly what we had done over here as well for polypropene. So this is exactly what we did. So let's try another molecule. I think it's this one. So I'm going to try and redo this, and we're going to see how the polymer would be formed. So again, remember, that's my molecule. Let me get rid of all of this. So there's this molecule which has a double bond in it. It's an unsaturated molecule. So what did I tell you? I told you that when you see a double bond like this one, I specifically told you that there should be nothing on the right side. So there should be, this side should be empty. So this CH3, take it upwards. I mean, twist it upwards. It shouldn't be on the right side. It should be pointing upwards. So I'm going to take it upwards. So that's what we're going to do. So instead of this CH3 over here, I've just bent it and I've taken it to the top. Remember, I did not break the bond. I did not change the molecule. The only thing is I just twisted it and sort of twisted it upwards. This one as well, this CH3 over here. This side should be empty. So I'm going to take it and twist it downwards. So this CH3, let's draw it over here. So here's my monomer, and simply draw more of them, copy paste this, keep them slightly further apart from each other, just a second. So they should be very close to each other. So I'm just taking them slightly away from each other, and I'm going to draw a 4th one. Usually in the paper you're being asked to draw just 2 of them. Just getting rid of this box. No need for that. That was just highlighting it. What's going to happen? The double bonds would start breaking up. They would turn into single bonds. Remember, under high pressure. This happens under high pressure and high temperatures. So double bond is gone, and now they're going to start linking up. The carbons, they need to make the 4th bond, so they all start linking up with each other. Remember to draw the continuation bond, showing that there's still stuff happening over here. There's still other monomers joining up. And the short notation would be just draw the repeat unit, which is this one. So I'm going to draw just the repeat unit. This is the thing that's repeating over and over again. I'm going to put brackets around it. You can put curly brackets or square brackets, doesn't really matter. Type in, that's the number of times it's going to repeat. So that's your polymer now. So you can see examples being done over here of different polymers. Now, remember there would be some specific examples that need to be remembered. One of them is PVC. Remember this. This is polyvinyl chloride. It's PVC. These are your plastic pipes, and I can show you stuff. A lot of stuff is actually now made from PVC. So let me just quickly show you PVC pipes. So that's, we're just Googling it, just finding images. 1 second. So here are PVC pipes. These are the ones that use, I mean, a lot of bathroom fitting, that's or house drains, etc. And even at the city level, a lot of PVC pipes are used for transporting different things. Then you make PVC. What do you make from PVC? You make PVC tiles as well. So right now, a lot of these fake wooden tiles are made from PVC. That's a plastic, and PVC windows are now being made as well. So most of these windows are made out of PVC. That's again looks like fake aluminium or but it's very good. It's very good. It's very tough and it's very durable. And you also make I mean, it's a good replacement for wood nowadays. So PVC doors as well. So you can see these doors being made from PVC, and it's very durable because it's plastic. Plastic, nothing happens to plastic, even if you uh, even if you uh, throw water on it. So PVC is really, really good, and it's strong. It's very unreactive, and it's also light. It's very light as well. So that's kind of a good thing. So lots of things are made from it, and this is the monomer of PVC. You should remember this. It's simply ethene, but with one of the H replaced by Cl. That's our monomer, and the monomers, they link up. So I'll just quickly show you. The same monomers are they're going to repeat. Actually, what I can do is I can uh, redo this. So this is how the polymer would be formed. Lots and lots of monomers, all hundreds of thousands of them, all linking up. The double bonds in between are going to break, so they're gone. And so the double bonds, they turn into single bonds, and the carbon atoms, they start making the fourth bond with the neighboring carbon atom, and they start linking up. So that's your PVC chain. It's your PVC polymer. Another one, that's PTFE. That's polytetrafluoro ethene, or Teflon, also known as Teflon. That's a plastic that's used. It's also unreactive. It's used as a non-stick in cooking utensils, and it's quite resistant to heat as well because the CF bond is very strong. So this is the monomer. It's again similar to ethene, but it's got fluorines attached to it. So the monomers, they all join up and they start linking up. The double bonds in between, they go away, and they all sort of link up. That's what PTFE is. So here are some more examples of different polymers. So we can try another one. Maybe it's going to be time consuming, but it's important. So let's try and do polybutene. So I'm going to do this on the side, polybutene. So again, the monomer is but. So that's 4 carbon atoms. 2-ene means that the double bond is on the second carbon atom in the middle. There's going to be an H, another H, and there's going to be 3 H's with this and 3 H's with this. First thing, redraw the structure. I told you that when you see a double bond, there shouldn't be anything on the right side or on the left side. So what I'm going to do is this CH3, I'm going to take it downwards. I'm going to attach it to the same carbon atom, but it's now pointing downwards. So I'm just twisting it. Similarly, this CH3 over here, I'm going to take it downwards as well. Shouldn't be on the right side. This side should be empty. So I'm going to take this below. So that's my monomer, and you link them up. So I'm just going to draw 3 of them just to be quick. So here's the third one, and forget the square bracket, and the double bond first is going to break under high pressures, high temperatures. So they all start to break and they start linking up. Conservation bond, And if you want to show just one repeat unit, so this is the thing that's repeating over and over again. That's it. Put square brackets or curly brackets around it and write N. That's it. So those are your addition polymers. Now remember, a few things about addition polymers is that this thing. Addition polymers are kind of really unreactive. They're very unreactive. I mean, you know about plastics like the polythene bags, etc. They're very unreactive. Like you can polythene bags are really good because you can put food in it and the food is not going to react. You can throw water in it; it's not going to react. So plastic is pretty good, but it has some harmful effects because it's very unreactive. It's non-biodegradable, which means that this thing over here, it's non-biodegradable, and by some estimates it's going to take hundreds of years for it to decompose naturally. So you see a lot of plastic bottles, etc., lying around. So they consume a lot of landfill sites. Like if you have cities and there's a lot of plastic being done, most of the trash around you, that's plastic. Everything is it's covered in plastic. You go to a shop, every wrapper is, I mean, it's mostly plastic. And most of the time it's addition polymers. So these addition polymers are kind of really harmful because to the environment, because they don't decompose, they don't biodegrade. So they consume a lot of landfill sites. A lot of land has to be used for dumping only, and that gets wasted. Burning them, you can burn them. They burn easily. You can see plastics burning, but that would cause a lot of pollution, greenhouse gases. There would be a lot of carbon dioxide emission. There would be a lot of global warming because of that. And you've got animals that can choke and die on them. A lot of animals, because a lot of the plastics that you're carrying, they have food sticking in them, and the animals are attracted to it, and they consume the food along with the plastic, and they eventually end up choking on it. Plus, it's non-biodegradable. So these are some of the harmful effects of addition polymers, to be very specific. So we're now going to study the next chapter, which is alcohols. And remember, alcohols have a general formula of CnH2 and plus 1 OH. So if you want to write the formula of an alcohol. Now, alcohols, what are alcohols? Alcohols have this particular functional group in their formula. It's a bunch of carbon and hydrogen atoms, but there's going to be an OH. And remember, it's always the O in the OH that is bonded or connected to the carbon atom. So if the OH is attached at the bottom, it's the O that's going to be attached to the carbon atom. OH attached on the right side, it's going to be the O that's going to be attached to the carbon atom. So this one is 2 carbon atoms. So this is ethanol. This one is 4 carbon atoms. So that is bute and butanol, and 2 represents the position 2, which is that the OH is attached on carbon number 2. Now, how does the general formula work? So for example, over here, N would be taken as 4 because you've got 4 carbon atoms. N is the number of carbon atoms, so it's going to be C4. And 4 into 2, 8, 8 plus 1, that would be 9. So it's going to be H9 and OH. So that is our general formula. So you can count it. It's C4, H is 3, 2, and 1 and 3. That's 9. And there is an OH group attached. So whenever you have an OH, at least one of them, you could have 2 multiple OH, that they would be called diols. You could have 3 OH groups, they would be triols. So those are your alcohols. Now the physical properties are kind of different from alkanes and alkenes. That the physical properties are kind of really high. The higher melting and boiling points. So most alcohols are liquids. I mean, you use alcohols a lot, especially for as disinfectants. They're volatile, but they're mostly liquids, and they're very soluble in water, so they mix very easily. And remember the same thing, as size of the molecule increases, remember this applies across all organic compounds, that as size of the molecule increases, the melting and boiling point, viscosity, it all increases. It becomes thicker, the melting and boiling points are higher, and the flammability, it becomes harder to burn them. So the flammability decreases if the size of the molecule becomes bigger. Now, the first thing is, how do you end up forming alcohols? We did one reaction earlier, which was the hydration of alkenes. That if you have a double bond in an unsaturated molecule, an alkene, what's going to happen is that the double bond is going to react with water, and the double bond would go away. turn into a single bond, and an H and an OH, as shown over here, will get attached. So an H and OH will get attached, and the conditions for this reaction are 60 atmospheres, 300 degrees centigrade is the temperature, and phosphoric acid is used as a catalyst. But industrially, more importantly, alcohols are produced in this way. This is a process known as fermentation. In fermentation, you must remember this equation. You take glucose, which is C6H12O6, and you ferment it. You put it in large barrels and you put it there for a while, and you ferment it. It changes into ethanol, which is C2H5OH, and carbon dioxide. Now, this one is not a balanced equation. We can also simultaneously try and balance it. So I think this would be balanced now. Now, the conditions for this reaction is that you would need yeast, which is a biological catalyst. So yeast does that when it respires, but it respires anaerobically, which means oxygen has to be absent. There should be no oxygen in the mixture. And so yeast would turn the glucose into ethanol. The temperature has to be 25 to 35 around room temperature, because a higher temperature would kill the yeast. It would denature the yeast. It's a biological catalyst, so it's a type of fungus, I think, and it's going to die if you increase the temperature. Usually reactions speed up when you increase temperature, but biological reactions, they usually stop when you increase temperature, because biological things, they get denatured. They stop their functioning. They get destroyed if the temperature is really high. And at lower temperature, the yeast is kind of inactive, so it's not going to work at lower temperature. So all these conditions have to be met. Remember, if oxygen is present, then the alcohol will get oxidized to carboxylic acid, and you'll get vinegar instead. So remember that point as well, that it has to be without oxygen, because if oxygen is present, you're not going to get ethanol. What you're going to get is vinegar. This is simply a graph of the rate of reaction at which this reaction happens at the optimum rate. That's 25 to 35. Remember, yeast dies at higher temperatures. Yeast is inactive at lower temperature. The next thing about this reaction is that the yield of the alcohol is extremely low. Extremely low. Why? Because as soon as the alcohol is produced, the alcohol, because it's a disinfectant, it would kill the yeast. So as soon as the alcohol concentration, it becomes 10% of alcohol, the yeast will die because of the alcohol. So eventually you would have to distill it. All the alcohol produced will denature the yeast. Distillation is done at the end to remove the alcohol. So once alcohol is formed, you're going to distill it to remove the alcohol from the mixture, because not a lot of that is going to get converted. It will be converted into alcohol. So you have to remove the alcohol, and you do it by distillation. The next reaction we're going to talk about is the dehydration of alcohols. Dehydration of alcohols is when an alcohol gets converted back to an alkene. So it's simply, you have an alcohol, it has an OH. The OH gets removed, and an H gets removed from the neighboring carbon atom, and instead you get a double bond between the two carbon atoms, and that turns into an alkene. And the conditions for the reaction are you either use aluminum oxide and heat, or you use concentrated sulfuric acid as a dehydrating agent. So I'm just going to do one example for this. So if I pick any alcohol, let's say I pick ethanol. So two carbon atoms, and there's going to be these hydrogen atoms attached to that alcohol. Now what would happen is the OH will be gone and the H will be gone from the neighboring carbon atom. Remember from the neighboring carbon atom. So the H gets lost from the neighboring carbon atom. Now the carbon atoms are short of bonds, so they're going to make a double bond between them, and that would turn it into an ethene molecule. So that's what's going to happen if you dehydrate an alcohol. So remember, again, conditions: aluminum oxide plus heat, or you can use concentrated sulfuric. You can bubble it through concentrated sulfuric acid, and you'll get an alkene. The next reaction we're going to talk about is the oxidation of alcohols. So what's the oxidation of alcohol? Oxidation, remember, if you just want to do a quick revision, is the addition of oxygen, or the removal of hydrogen, or in technical terms, it's the loss of electrons. So you have an alcohol over here, an ethanol molecule. Remember, every time the reaction is going to be exactly the same. What's going to happen is that this carbon, which is right now attached to an OH, you oxidize it. So this O represents an oxidizing agent. You oxidize it, so this carbon atom, oxens get added to this carbon atom and H get removed. So this carbon atom turns into a carboxylic acid. An oxen atom gets added and the two hydrogen atoms, they get removed. So it turns into serial bond O and OH. And as a byproduct, a water molecule is also produced in the reaction. So you can take any alcohol, just focus on the carbon that's bonded to an OH. And the oxidation only happens for that carbon atom. Nothing happens to the rest of the molecule. So this carbon atom, it turns into a carboxylic acid. That's it, serial bond O and OH. And any alcohol, wherever you see OH, it would turn into a carboxylic acid. Now, and remember, water is a byproduct. Now, this represents an oxidizing agent. An oxidizing agent is something that does that. So you've got two oxidizing agents, two popular oxidizing agents in chemistry. One of them is K2Cr2O7, which is potassium dichromate 6. It should be acidified. There should be acid added as well. And you reflux it. And it changes from orange to green. The other one is potassium mangnate 7. And again, you use KMnO4, acidified. H plus 1 represents an acid, and you reflux it, and it changes from purple to colors. You must know the color changes that would happen as well. So potassium dichromate 6 would always change from orange to green, and potassium mangnate 7 would always change from purple to colorless. Now, reflux, I'll just quickly explain what reflux is. I'm just going to Google reflux apparatus in chemistry. So just 1 second, hopefully we'll get that. So let's try and go with this one. So this over here is, and I'm going to copy this 1 second. So I'll just copy it here just to explain what reflux is. So this one, we have this image over here, and just trying to explain what reflux is. Remember, reflux is simply heating it, right? You heat the reactants. That's the basic idea. When you hear the term reflux, you're heating it. But the problem is that heating alcohols is kind of difficult because all the alcohols, they would tend to evaporate. So if you have an open container, the alcohol vapors would eventually evaporate. You don't want them to evaporate. You're just trying to heat them, because if they evaporate and they escape, they're going to just go into the air, and you're going to lose all the alcohol. So we're trying to oxidize alcohols. We're trying to heat it with an oxidizing agent, and we don't want the alcohol vapor to escape. So you put a condenser on top. That's it. You put a cold condenser on top. So if by any chance any of the alcohol evaporates, it's going to condense right back because of the cold environment in the condenser. They're going to lose energy and the molecules would fall back into the container. So it's a way of heating a substance without losing it, without it getting evaporated. Like if you're trying to heat water to a high temperature and you want to heat it, water would evaporate as well, and you'll be left with nothing. So you'll put a condenser on top, and you'll ensure that if any water evaporates due to the cold environment, the water is going to fall back into the container. So reflux is simply heating by just putting a condenser on top. Actually, we have a diagram over here already. So it's a method of heating. That's it. And why do you do that for alcohols? Because alcohols are kind of very, very, very volatile. So they evaporate very easily. You don't want them to escape. So that is about alcohols. So now what we're going to discuss are carboxylic acids. Carboxylic acids, that's pretty much we're almost ending organic chemistry. We have to do esters as well, and polymers after that, condensation polymers. So carboxylic acids have this particular functional group. R is the rest of the molecules. It's a bunch of carbon and hydrogen atoms, and it has serial bond O and OH. So any molecule that has, so I can draw a few of them. So for example, I've got a molecule having 3 carbon atoms, and if this molecule has serial bond O and OH group attached to it, then it's a carboxylic acid. This is the rest of the molecule that I'm representing with an H, so I can, with an R, sorry, so I can add all the other hydrogens, and that's it. That's a carboxylic acid molecule, and this is my, it's a 3-carbon atom carboxylic acid molecule. So it's going to be the name is going to start with prop, and this one is propanoic acid. This one is ethanoic acid, 2-carbon atom, C double bond O NOH, and this one is 4-carbon atom, C double bond O NOH. So as long as you have this C double bond O and OH thing going, that would be your carboxylic acid. Now, one thing about the general formula of carboxylic acids, let's discuss that very quickly. The general formula of carboxylic acid is CnH2n plus 1 COOH. This thing is referred to as, like if I mark this, this thing over here is your C and O and O and another H. So that's your COOH group. So it's CH3, CH2, COOH. Hence, it's RCOOH, or you can write it CnH2n plus 1 COOH. That's the general formula. Remember, what is N in the general formula? Like if you don't want to draw the structure of the molecule, you can simply just use the general formula, and that will give you the formula of the molecule. So, for example, N is, remember, number of carbon atoms, but minus 1. So it's 1 less than the number of carbon atoms. So, for example, I'm trying to draw. Let me try and draw a molecule of propanoic acid. Let's do propanoic acid. So that's 3 carbon atoms. So the number of carbon atoms, that is 3. What I'm going to do is I'm going to take, so the number of carbon atoms is 3. So what I'm going to do is I'm going to take N is equal to 2. So if I use N is equal to 2, it's going to be, focus on the general formula, it's going to be C2. H would be 2 into 2 plus 1, that's 5. So it's going to be C2, H5. So C2 and H5 and followed by COOH. So that's my propanoic acid molecule. So if the number of carbon atoms is 3, you're going to take N is equal to 2. Put this in the formula, you'll get this. And you can match this. This C2H5COH is the same thing. C2, this is C2H5 and COH. Propanoic acid, you can either draw the molecule or you can just use the general formula, that's it. So remember the general formula, and remember this thing that that N is going to be 1 less than the number of carbon atoms. So let's move on to the physical properties. So the physical properties of your carboxylic acid molecules are kind of the same as alcohols. They have high melting and boiling points. Here are some carboxylic acids that you should remember. Ethanoic acid is vinegar, also known as acetic acid. You've got malic acid in apples. You've got citric acid. You've got amino acids. That's what you are made of. Proteins are made of. So they've got high melting and boiling points. Another thing about carboxylic acids is that they ionize weakly and are considered weak acids. So they are acids. That's another property. What's an acid? An acid is something that donates a proton donor, which basically means it produces H plus 1 ions. So this carboxylic acid is capable of producing H plus 1 ions. But it's a weak acid, which means that it only ionizes, it only does that very, very partially. It just does this, ionizes very weakly. So it's a weak acid. And let me show you the ionization of this acid. So for example, you've got ethanoic acid over here. So that's 2 carbon atom, double bond O and OH. Focus on this OH over here. This OH is the thing that's going to ionize. The OH would break. It would ionize. It's going to break in the middle, and the molecule would split into 2 parts. There's going to be this CH3C double bond O and O minus 1 ion, and the H plus 1 would leave it. So that's how it's acting as an acid. It's producing H plus 1 ion. So which is why it's acting as an acid. That the H over here, this one breaks off. So nothing happens to the rest of the H. It's only this H at the end that's going to break off. So it's going to be this ion plus H plus 1. So if it's ethanoic acid, this ion would be known as it's known as the ethanoate. So it's known as the ethanoate ion. The condensed form is this one, CH3. Like if you want to use the general formula, it's going to be CH3COOH. And the last H, the OHH, would break off. So it's going to become CH3CO minus 1, and H plus 1 would leave it. And that pretty much happens with all acids. So for example, even the ones that we drew earlier, like these ones, this H over here is going to break off. Not all of them. Happens very weakly. This H would break off. This H would also break off, and the H plus 1 would go away. It would leave, and it's going to produce. So the H plus 1 would leave, which is why it's acting as an acid. I mean, this H would go away, and you'll have a propanoate ion. There's going to be a -1 charge left over here, a -1 charge over here. This is methanoic acid, so that's one carbon atom, double bond ONOH, and it would form a methanoate ion. So let's move on, and let's start talking about reactions of acids. Now, since it is an acid, although a weak one, the first reaction that you studied for acids was that a metal reacts with an acid to produce salt plus H2. So remember this reaction, a very basic reaction. Remember also that not all metals are going to react because metals have a reactivity series. Some are very reactive, some are very unreactive. So the metals that are above hydrogen in the reactivity series are the ones that are going to react. So note that down. Metals that are above in the reactivity series, they're the ones that are going to react. And so that includes K, Na, Cm, G, Al, Zn, Fe, S, and Pb. And then H is followed. So copper would not react, but metals above H in the reactivity series. Mazet metals are the ones that react very well. Very reactive group 1 metals would react explosively. So what happens when a metal reacts? The Mg is going to come. It's going to knock out the H in the acid and take its place. Mg is +2, Cl is -1. So if you crisscross, it's going to be MgCl2. And H2 gas is formed. Calcium comes in, phosphoric acid, it knocks out the H. Calcium takes the place of the H, and calcium and phosphate. Calcium is +2, PO4 is -3. So the formula is Ca3, PO4 twice, and H2 is produced. Now for carboxylic acid, something similar would happen, that if I react sodium with butanoic acid, butanoic acid has 4 carbon atoms, so I'm going to take N is equal to 3. I'm going to put 3 in the general formula, and I'll get the C3H7. And C double bond ONOH. So Na is going to come in. And remember, we just talked about this H leaving. So N is going to come and knock out that H. That would form H2 gas, and Na plus 1 would take its place. So it's going to become, this was butanoic acid, so this one would become sodium butanoate. And similarly, we can have other reactions. We can do a few of them. So magnesium plus methanoic acid. Methanoic acid is going to be, I can use the general formula, which is CnH2n plus 1. And there is COOH. Now, if carbon is 1 in methanoic acid, N would be taken as 0. So it's going to be 0 Cs. And 0 into 2 is 0 plus 1, that's 1. So H would be 1 and COH. So that's the general formula. Or you can just draw the formula, which is C double bond ONOH, just 1 carbon atom. So to complete the bonds, you're going to put in an H atom over there as well. So what's going to happen? Magnesium would come in, and magnesium is going to knock out or replace the H. So magnesium comes in, Mg is +2, group 2 is +2, so HCO -1. You crisscross, it's going to be HCO twice. And Mg is going to be once, so plus H2 gas is produced. Similarly, aluminium with ethanoic acid, something similar happens. This is ethanoic acid. Again, if you eth would be, the number of carbon atoms would be 2. So you're going to take N is equal to 1, and you're going to put that in the general formula. So it's going to be CH3COH. Aluminium would come in, and it's going to knock out the H. So CH3CO -1, and aluminium is +3, so you crisscross, and it becomes CH3CO -1 brackets 3, and this would be aluminium ethanoate, and H2 gas is going to be produced. So a salt would always be produced in this manner. It's always going to be produced. The H in the carboxylic acid is going to get knocked out. So all the other reactions, let's talk about reaction number 2. We have a base plus acid reaction, which is going to produce salt plus H2O. So what's a base? Base is metal oxides and metal hydroxides, and you can also add other bases as well, let's talk about, I mean, we can add ammonium hydroxide as well to it. So we're just talking about oxides and hydroxides at the moment. So sodium hydroxide reacting with this is propanoic acid. So the H would be knocked out by Na and it would form a salt, which would be sodium propanoate, because you formed a salt from propanoic acid. So it's going to be sodium propanoate plus water is going to be produced. So base plus acid produces salt plus H2O. NaOH plus sulfuric acid is a similar reaction. Na comes in, knocks out the H, Na2SO4 plus H2O. So calcium hydroxide comes in. You've got, I think this is pentanoic acid because you've got 5 carbon atoms, 4 over here, 1 over here. Calcium comes in, knocks out the H. Calcium is 2 plus. This is minus 1. So what happens? You get a salt. You get a salt of calcium propanoate. This is plus 2. This is minus 1. Crisscross. So there's going to be a 2 over here. And water molecules are going to be produced. Similarly, you've got a carbonate plus acid reaction and a metal carbonate or an ammonium carbonate, so K2CO3 reacting with phosphoric acid, salt is produced in the same way. The K comes in, knocks out the H. K3PO4 is formed because this is minus 3, K is plus 1, so crisscross, it's going to be K3PO4 plus water plus carbon dioxide are produced. Now, if the same carbonate, K2CO3, reacts with ethanoic acid, K is going to come in, knock out the H gets knocked out, K takes its place and water and carbon dioxide are produced. Now in this reaction, remember when gases are produced, you're going to get effervescence. You're going to see bubbles being produced in the solution. Last one. So I've got ammonia plus acid and it produces ammonium salt, NH3 plus HCl. Knocks out the H, NH4 plus 1 takes its place. Same thing happens with butanoic acid. NH3 comes in, knocks out this H and forms ammonium butanoate. That's it. So let's try and see if we can practice a few. So that's about it. These are the 4 reactions I did, and we can just do some random reactions over here. Let me just do a reaction of let's try methanoic acid, again CN, H2N plus 1, and it's COH. So methanoic acid is carbon is 1, so N would be taken as 0, and you're going to have 0 C's and H would become 1, and there's going to be C double bond O and H. So I'm going to try and react it with, let's say, barium hydroxide. So this one is barium is plus 2, OH is minus 1. So this one is a base plus acid reaction. The H in the methanoic acid would get knocked out by barium. So it's going to be barium would take its place. Barium is 2 plus. So crisscross. So this thing would become 2 plus. There's going to be H2O plus. There's going to be carbon dioxide that's going to be produced. Let's do another one. Let's do propanoic acid. So prop is, there's going to be carbon would be 3 in prop and N would be taken as 2. So it's going to be C2, NH5 and COH. So C2, H is 5 and it's going to be C double bond O and OH. Plus I'm trying to react it with what? Let's do it with MgCO3, carbonate. So salt, water and carbon dioxide is produced. Salt is going to be produced in the same way, just replace the H at the end with Mg, which is 2 plus, and you're going to put 2 over here. And you're going to have water plus carbon dioxide as your product. So that's it. So I'm not going to go further into this. You can find more lectures specifically on this on my channel. So I'm going to just move on. So this one, last point, physical properties. Carboxylic acids, they conduct electricity in aqueous state because they have free moving ions. So we just told you that a carboxylic acid would break up into ions. So your solution is going to have charged particles. It's going to have negative ions. It's going to have positive ions. And those ions will conduct electricity. But remember, they ionize weakly. So focus on this point as well. that they don't ionize a lot. So they're kind of poor conductors of electricity. They do conduct electricity, but they don't have so many ions because they ionize very, very weakly. Like if you have 1,000 molecules of carboxylic acid, very few of them are actually going to end up ionizing. So let's finally move towards esters now. You've got esters, which are kind of these sweet-smelling, oily liquids, uh, and they use frequently in food flavors. Like most of the food that flavors that you see, like if you see a strawberry ice cream, then it probably doesn't really have anything to do with strawberry. They probably created an ester somewhere in the lab that smelled and tasted like a strawberry. Similarly, vanilla, or so a lot of these food flavors that you have in your food, they're just artificially made esters, which have a particular smell. They have a particular taste. So they use as food flavors and perfumes. Remember that that's one of the number one. That's the number one use of an ester. So what is an ester? An ester is this thing. Somewhere in the molecule, there's a acetyl bond O and O, right in the middle, and there's got to be a carbon chain on this side, and there could be an H or a carbon chain on this side. Carbon chain is referred to as an alkyl chain. So, for example, this is one example of what an ester would look like: acetyl bond O and O in the middle, carbon chain on this side, carbon chain on the other side. So I can make another one. Let's try and make. I can have C double bond O and O, and I could put one carbon over here, and I can have one H on the side. This carbon will have three hydrogens to complete its bond, so that's another ester. So as long as you have this particular group or structure, it is an ester. Remember just this point, that there should be no H on this side, because if there was an H on this side, then it would instead be a carboxylic acid. It would instead be acetyl bond ONOH. That would be a carboxylic acid. We don't want that. It has to be a carbon chain on this side with the O over here. So let's figure out how esters are made. First thing, let's focus on this particular. Let's highlight this. Very important. So let's focus on this. An alcohol is going to react with a carboxylic acid. So what's an alcohol, which we have already done previously? So an alcohol is any molecule that has an OH only. What's a carboxylic acid? It's any molecule that has C double bond O, and it's got an OH as well. So that is what a carboxylic acid is. So the two things are going to react together, and the two things would react together, and they would form an ester and a water molecule. It's a condensation or an esterification reaction. Why is it a condensation reaction? Because when an ester is formed, a water molecule is produced as well. So whenever water molecules are produced, that's a condensation or esterification reaction. And the conditions for that, note down the conditions, really, really important. It has to be reflux and concentrated sulfuric acid. So we just did reflux. Reflux was that alcohols were kind of very volatile. So somewhere above, we did actually go through reflux. This was reflux. Reflux simply means it's a method of heating. That's it, and it's a method of heating to prevent volatile substances from boiling off. You don't want them to escape, so you put a condenser on top so that anything that boils off falls back into the container and is not allowed to escape the container. So that is what reflux is. You heat it with a condenser on top so that any vapor. Alcohols are very, very volatile, so you don't want alcohols to kind of evaporate. So let's move on quickly. Where were we? We were at esters, and we were at this box. So that is how esters are going to be made: reflux and concentrated sulfuric acid. The other thing is that it's a reversible reaction, which means the reaction could happen in the backward direction as well. The ester could be hydrolyzed. This is hydrolysis of esters. Water molecule can be added back, and alcohol and carboxylic acid could be reformed. So for that, you need dilute acid plus reflux. So that's acid hydrolysis, and there could be dilute alkali like NaOH plus reflux. So that is alkaline hydrolysis. So you have two types of hydrolysis: acidic hydrolysis. So you can use H2SO4 and reflux dilute, or you could use dilute NaOH and reflux. In both cases, the ester would break and the water molecule will get added back again, and alcohol and carboxylic acid are going to be formed. So we're going to talk about the reversible reaction a bit later. Let's figure out how esters are made first. So the way esters are made is that you take an alcohol, it has an OH. You take a carboxylic acid, it's got a C double bond O and OH. Make sure the two functional groups are pointing next to each other. The carboxylic acid would lose its OH, and so the H and the OH of the carboxylic acid, they are going to be lost from the middle. So they've been removed from the middle over here, and instead the H and OH, they would join up. They would end up forming a bond. So I'm just going to show you how this would happen. So let me just quickly redo this and show you how an ester would be formed. So I'm going to draw the alcohol and the carboxylic acid back again. So here we go. And what I'm going to do is I'm going to remove the H and the OH that was in the middle. So that's gone. So the alcohol is without its H, the carboxylic acid is without its OH. The atoms are now missing bonds. So what you're going to do is you're going to connect the two together. So the C and O will get together and they would form this ester link. So that's known as the ester functional group, C double bond O and O. C double bond O and O, that's an ester link. Plus a water molecule is going to be produced because the H and OH that were lost, they have now ended up producing a water molecule. So you can make esters, and we can do a bunch of esters right here. Let's focus on ethanoic acid. Let's do ethanoic acid. So ethanoic acid is 2 carbon atoms and it's got double bond O and OH, and this one will have 3 H's. So that's ethanoic acid. I can take an alcohol. Let's do propanol. Now remember, the OH must be pointing, the two OH must be together. So I'm going to draw this molecule the other way around. So there's going to be CH. So these would all be H's. And the two are going to join up. And the two are going to join up. So we're going to do just that. We are going to, let me just put the arrow up, move it down. And I'm going to connect the two together. So what I'm going to do is I'm going to just redraw everything. Everything pretty much remains exactly the same. So here are my two molecules. The H and the OH are going to be lost. The alcohol would lose its H. The carboxylic acid would lose its OH, and the alcohol would lose its H. So they would be gone. I'm going to rub them off. They have ended up forming water molecules. So let's be careful. So they've ended up forming water molecule. They've reacted together, bring the two together, and connect them with each other. So C double bond O and O. So that's now your ester link, which has been formed. And a water molecule is going to be produced as a result. So that's simple, pure esterification. So that's your ester. So you can make all sorts of esters, which we have shown over here. So here's methanoic acid reacting with ethanol. So methanoic acid is 1 carbon atom, double bond O and OH. Ethanol is 2 carbon atoms and it's got an OH. So the OH is lost, the H is lost, and the two end up reacting together, forming a water molecule. And in the middle, the space that's left, the two would link up. The two molecules, this O would link up with this carbon atom, and I can quickly show that again. So let me just quickly show what's going to happen. So just 1 second. I'm going to paste this. So here I've pasted the two molecules together, and I'm going to get rid of the H and get rid of the OH, and I'm going to bring the two molecules together so that they link up. So the two are going to link up in the middle. And that's our ester. Plus, obviously, a water molecule is produced as well. So that's how esters are going to be formed. So I've shown you a bunch of other, let's do another one. This is, I think, butanoic acid, and this is propanol. So the OH and H are lost, and they're going to form an ester in the middle. That's an ester. This is the condensed version of this. It's CH3, CH2, CH2, CO, and O. So if you get two O's in the middle between the two carbon atoms, that's probably an ester, followed by CH2, CH2, CH3. We can write the condensed version of this one as well, which is HCOO. So it's HCOO, CH2 and CH3. So that's the condensed version. Or you can just combine the two oxygens together as well, and that would end up forming CO2. We're going to also talk about naming esters. That's also kind of very important. So the naming is done in two parts. When you make an ester, you get a side from a carboxylic acid, you get a side from alcohol. The double bond O side, so here's how you're going to name them. The double bond O side is the one, you're going to name this in two parts. You're going to divide it in the middle, name it in two parts. You've got around the ester link. You've got one carbon atom over here, so that's your meth, one carbon atom. And you've got two carbon atoms on the other side, so that's your eth. So the two sides are going to be named separately. This would be meth and this would be eth. The carboxylic double bond O side would be followed by O8. So it's going to be called methanoate. And the single bond O side would be referred to as vial. So it's going to be methyl, and the name would be ethyl methanoate. So you're going to follow the same naming structure for every molecule. If we have it over here, just one second. Let's try and name this molecule. You're going to focus on the two sides around the ester link. That's your ester link. Two carbons over here, so that's our eth. And I've got four carbon atoms on this side, so that's my bute. Four carbon atoms is bute. What would the name is anyway? If the single O side is the vial side, you add vial, and the double bond O side is the OH side, so it's butyl ethanoate. Same thing again. Let's repeat. Here's my ester. I've got four carbon atoms on this side, and I've got three carbon atoms on this side. So three carbon atoms is prop. Four carbon atoms on this side is bute. Double bond O side, that's O8. The single O side would be vial, so it's going to be propyl butanoate. So that's how esters are going to be named every time. So we can even try and draw a few esters. So if I give you a molecule of any molecule, let's say ethyl and methanoate, and somebody is asking now, just looking at the names, you should realize that that's an ester. So that's an ester that's got C double bond O and O in the middle. I mean, that's confirmed. It's an ester. So the carboxylic double bond O side, methanoate. So that's meth is how many carbons? That's one carbon. So this side over here is going to have one carbon atom. It already has one carbon atom. So I'm just going to put an H over here. The other side is ethyl. So that's eth. Eth is two carbon atoms. So this side over here is going to have two carbon atoms. You can add the hydrogens. This one will have a total of three hydrogens. This one will have a total of two hydrogens. So that's my molecule. We can do a similar one. Let's talk about pentyl ethanoate. So pentyl ethanoate. Now pent is five carbon atoms, and ethanoate is two carbon atoms. So again, starting off with our basic structure, that's an ester, C double bond O and O. So we have our C double bond O and O. Pent is five carbon atoms. So pentyl. Wild side is the single O side. So there should be 5 carbon atoms on this side. That's 1, 2, 3, 4, and 5. And ethanoate, that's eth is 2 carbon atoms. So we already have 2 carbon atoms. The double bond O side is going to have 2 carbon atoms. So we're done with our 2 carbon atoms, and we can add in the hydrogen. So they're going to be 3. They're going to be 2 hydrogens with this, 2 hydrogens with this, 2 hydrogens with this as well, 2 hydrogens with this as well, and this carbon needs 4 bonds, so there should be 3 hydrogens with this. So that's simply your ester, which is going to be referred to as pentyl ethanoate. So hopefully esters is clear. You need to practice a lot. Esters are kind of important. You got a lot of questions on esters. So please practice a lot. You can watch the other lectures as well in detail, where I talk in detail about esters. But this one is a quick crash course. So we're going to move towards the next topic. So let's now talk about condensation polymers. Condensation is the reaction in which a molecule of water is produced. So polyesters. So we're going to talk about condensation polymers. I'll just briefly describe to you that there are going to be 3 types of condensation polymers. We did addition polymers earlier. Now condensation polymers, you've got amides, polyamides, you've got polyesters, and you're going to have complex carbohydrates. So these are your 3 types of polymers. So we're going to start off with polyesters. Poly means many. So it means lots of esters. It means lots of these things. We just did esters, acetyl bond ONO. So it's going to be a long chain. And remember what a polymer was. We previously had discussed what a polymer was. I told you that what's a polymer? They're basically a bunch of small molecules, which are known as your monomers. So there could be any type of small molecules. So there are different types of monomers, and there could be thousands of them. Under certain conditions, what happens is that the monomers, they start bonding with each other. They start linking up. They start joining. So thousands of them would join up, forming this long thread-like structure, this long, really, really long chain. And that's what your polymer is. So it's a bunch of it's many monomers that have joined together to form that polymer. So starting with polyesters. Polyesters are first examples. You've got terylene. Remember terylene, that's frequently coming in your exams. Terylene is a fabric. I mean, you must have heard about polyester clothes. If you read the back of your sweater, most of the sweaters that you wear, they have polyester in them, your pants, your shirts, etc. If you read the fine print that's attached to it, a lot of it has a mixture of polyester. So it's frequently used in clothing and fabrics, and one real world polyester is fats. They're also a type of polyesters. So first thing, how is a polyester formed? So it's kind of similar to what an ester is, except for the fact that it's now a polyester. It's now many esters. Now, one molecule, one monomer, the first monomer, that's going to be a diol. A diol is a molecule which I'm going to represent with a box. I don't care what the molecule is. The molecule could be anything. It could be CH2 with an OH on this side, and it could be an OH on this side. I don't care what's in the middle. I just don't. So I'm just putting a box there. But the important point is that the molecule must have 2 OH groups pointing in both sides, and there has to be a dicarboxylic acid. So again, I don't care what's inside this box, what's going on over here. I need a molecule that has a carboxylic acid group on one side and a carboxylic acid group on the other side. So it could be any dicarboxylic acid. For example, I could have this could be a dicarboxylic acid. Like I can have a double bond O and OH over here, and I can simultaneously have a double bond O and OH on this side. So I don't really care what's inside this box. I don't care. It could be anything, except that I want that the molecule must have a carboxylic acid group on one side and a carboxylic acid group on the other side. Most of the questions that you're going to get would be in this box representation. So you have a dicarboxylic acid, and there would be alternatingly many diols and many dicarboxylic acids, and they would all start to eventually link up. So just to show you, I'm going to rub this off and do this again. What's going to happen is they're going to form an ester link. So let's copy this. So let's copy this and let's try and form the ester. So esters are formed when the H and the OH are lost. So the H from the alcohol, the OH from the carboxylic acid, they would all be lost. So the H is lost, the OH from the carboxylic acid is lost, the OH is lost, and the H is lost. And all these things, they would start to link up with each other. So they would start joining up. This O and this C, they're short of bonds now. This carbon would bond with this O. This O would bond with this carbon atom. This carbon atom would bond with something on the right side. This O would bond with something on the left side. So the chain would continue, and there would be lots and lots of ester links being produced. So there's going to be an ester link over here, and there's going to be an ester link over here as well. Serial bond O and O. O and serial bond O, that's an ester link. Serial bond O and O. So you're going to get all these ester links. And remember, these ester links are biodegradable, so they're kind of very good as well. That they decompose easily. So unlike addition polymers, which we studied earlier, they were not biodegradable. These ester links are they kind of naturally exist in your body as well, and they biodegrade easily. So they're the kind of plastics which are very good and very biodegradable, and they won't last for 500 years, and you don't need dumping sites for that. So these are all really good. They have good properties. So here's one example where I did not show boxes. I mean, I can get rid of the boxes. So I can get rid of the boxes, and I can make this. I can delete this and redo this. So let's try and redo this. So here are my diols. So I've got OH on both sides, right? There's a molecule that has OH on both sides, and I've got a carboxylic acid group on both sides. So I've got a dicarboxylic acid and I have a diol. So this one is without a box representation, but the same exact thing would happen, that the two monomers would alternatingly repeat. So they're going to alternatingly repeat. And the same thing kind of would happen, that the H and OH would be lost. The OH would be lost from here. The H would be lost. The OH from the carboxylic acid would be lost, and the H would be lost. The H would be lost. The OH from the carboxylic acid. The OH would be lost, and the H from this side would be lost. And we can start removing them. So let's start to carefully remove all of them. Here you go, the H is lost, the OH is lost, the OH is lost, and the H is lost, and they would start to interlink with each other. So the double bond O would connect with the O from the other molecule, and they would start interlinking, and you have to draw this, make sure you draw this continuation bond, so you get all these ester links in between. So if I want to turn this into a box representation, what we were doing was we don't really care what's in between the two groups, which I was previously representing by boxes. So I don't care what type of molecule you have, as long as it is a dicarboxylic acid and a diol. So that's my polyester. So remember the examples, remember Terylene, remember everything about polyesters, remember how to actually draw these polyesters. And if you're being asked to draw repeat units, so what's being repeated over and over again, you're just going to copy this part. This is the part that's repeating over and over again. You're going to write this or copy this and put brackets and put N around it. That's my polyester. Let's now try and move towards polyamides, which are kind of, let me put this right. So polyamides, kind of similar like polyesters, but the monomers are different. So remember the monomers, one of them is a diamine. So it's a molecule, which I'm again showing with a box. It's a molecule that should have NH2 groups on both sides. N and H on this side, N and H on this side. And again, this is the same old carboxylic acid. There has to be a molecule that has carboxylic acid groups on both sides. So again, diamine, dicarboxylic, it just keeps on going alternatingly. So it's going to be, so you have to remember this, memorize this. Diamine, dicarboxylic acid, diamine, dicarboxylic acid. And pretty much the same thing happens. And that's again, let me delete this just to show you how this word happened. So just getting rid of the working which we had already done. And I'm just going to copy this just to show you how this would. So how this would go down. So as you can see, the H and the OH, the carboxylic acid loses its OH, the amine loses its H. H, OH, they're going to be lost. They're going to turn into water molecules. So let's start removing them. So the H and the OH goes. The H goes, the OH goes. The H is lost and your OH is also lost. The OH is also lost. And all of them, they would start so they would start to link up. And N would link up with acetyl bond O would link up with N would link up with acetyl bond O, and the acetyl bond O would link up with something on the right, the N would link up with something on the left. It's going to be a long chain, so it's going to endlessly just continue on and on, similar to this. So this over here is going to be referred to as your amide link, which is why these are called polyamides. This would be referred to as our amide link. So it's going to be NH and C double bond O. So whenever you see this, or the condensed notation is NH and CO, or you can write CO and NH the other way around as well. Doesn't really matter. So this, whenever you see this linkage, make sure you're able to identify the polyamides. So I'm just going to show you some of them. For example, let's just Google polyamides. And we're going to get a bunch of images. And I'm actually interested in structures, not the actual material. So here you go. So you've got, for example, look at this molecule. It's a complicated molecule, but you can see the amide link. There's NH and acetyl bond O, NH and acetyl bond O, NH and acetyl bond O. So there's NH and acetyl bond O. So there's this long chain going on, and they're all connected together. So you should be able to identify these polyamides. This one kind of clearly shows what's going on. So you should be able to, let's go back a bit. So you should be clearly able to identify these amide links whenever you see acetyl bond O and NH. So going back to this, let's go back, let's set this up again. Now going back to this, that's your amide link, and the examples are, you're going to get two types of these polyamides. One is synthetic, that's the laboratory made or industrially made. These are nylon, fishing nets, ropes you make out of those. You've got Kevlar, you've got bulletproof jackets and vests. So this nylon is kind of a really, really good, useful material, and it's again it's biodegradable. It kind of decomposes quickly. The natural one is proteins or polypeptides. We are basically kind of a polyamide. All animals, plants, etc. Proteins play a very major role in building cells and building muscles, etc. So naturally, we have a lot of polyamides in our body. So let's quickly discuss proteins for a second. Now, proteins are kind of slightly different. Just one second. So let's talk about proteins. Hopefully you can see this. So let's talk about proteins. Now, proteins are kind of they're unlike synthetic polyamides. They're not made out of diamines or dicarboxylic acids. Their monomers are different. They're made from amino acids. So the question is, what is an amino acid? So there's a minor difference. You're going to get pretty much the same thing, but the monomers are different. So go back and have a look. For polyamides or synthetic polyamides like nylon, let's even write that. This is for nylon specifically. So for synthetic polyamides, you've got NH, amines, diamines, and you've got dicarboxylic acids. You've got two different types of monomers. They're going to ask you about this. What's the difference between synthetic polyamides and what's the difference between natural polyamides like proteins? So they're made from two completely different, two separate monomers. On the other hand, you've got proteins, right? Proteins are made from amino acids. So there's only one type of monomer. So amino acid is a molecule that has a carboxylic acid and it has an amine both in the same molecule. In the previous case, we had two different monomers, one having carboxylic acids on both sides, the other one having amine on both sides. Now we have a single monomer. It has carboxylic acid on one side and an amine group on one side. So which is why it's called an acid, as well as amine, which is why it's called amino. So it's amino acid. So you're going to have these amino acids, lots of them. There are like 21 different amino acids in the human body. The only difference is every time there's something else in between. So we can quickly have a look at the structures of amino acids. Just to give you, you don't need to remember this, just to give you a general idea of what an amino acid would kind of look like. So if I can open this image in a new tab, so we have this. So this is not a good image so far. Just one second. So amino acids. Just wanted to show you. This should work, I think. Image in new tab. Just a second. Again, it's a pretty bad image. But the only difference is, so I'll just go back. I can't really find an image. So I'll just give you an idea that every time you've got 21 amino acids or 19 or 21 amino acids that make up the human body, the only difference is that the middle part is different every time. But every time it's going to have a carboxylic acid and amine on both sides. And the same thing would happen. So let's delete this and let me show you the working again. How to get the or construct the polyamide or polypeptide, also known as polypeptide. Remember that as well. So here is my copied version of this. And the OH would be lost, the H is going to be lost. The H of the amine would be lost, the carboxylic acid loses its OH, the H from the amine would be lost, the carboxylic acid loses its H, and so on. It just continues. So, and they would all start to link up, and serial bond O links with NH, serial bond O links with NH, serial bond O links with NH, serial bond O goes on, further links with something else, and over here as well. So that's our amide link. That's how we are getting the C double bond O. And NH. So you have these amide links, lots and lots of amide links that are pairing, and that is kind of not that different. I mean, this looks not that different from a synthetic polyamide, the one that we did over here. It's also got serial bond and NH, and there's a long list. One way to identify a synthetic polyamide is that if you look at the molecule, on both sides you have the same type of things. NH, NH, this box, there's serial bond O, serial bond O. So the only difference between the synthetic and the natural polyamide or protein is that in this, the box has different things on both sides. This has different things on both sides. At the end of the day, you still get an amide link. So this is known as a protein or a polypeptide. And what you can also do is you can break this protein back into amino acids. That can also be done. That's known as hydrolysis. So this one is known as hydrolysis, and you just need to heat it with HCl. You can boil it, and so most of your like if you eat meat, uh, if you put acid in it, it breaks down, which is why it's easier to eat meat. So that's how you marinate things, etc. So you can hydrolyze the proteins, or you can break them into smaller pieces. Anyways, so remember, what's a protein? What's a synthetic polyamide? The very last one that we're going to do is they're going to be known as complex carbohydrates, which are also known as starch. So they contain carbon, hydrogen, and oxygen only. And whenever you have a carbohydrate, the hydrogen and oxygen ratio is always 2:1. So what's a complex carbohydrate? It's made of glucose. Glucose, remember, is C6H12O6. So it's a molecule that has OH groups on both sides, molecule that has OH groups on both sides, molecule that has OH groups on both sides, and so on. This is what an actual glucose molecule looks like. So, I mean, we don't care what this is. So it's a molecule that has OH groups on both sides. So the molecule is kind of complicated. This is C6H12O6. But remember, it's going to have OH groups on both sides, just like the box representation that I've shown over here. Condensation reaction happens. Water is removed, H and OH are removed, H and OH are removed, H and OH removed. The only thing that's remaining now in the middle is this oxygen. So this is how a carbohydrate or a starch molecule would look like. And if you want to draw the repeat unit version of this, so you just take one, and you just repeat that over and over again. So the other representation is you just put square brackets, draw continuation bonds, and write N around it. That's about it. So glucose molecules all linking up, H and OH getting removed, and the only thing that's left is oxygen in the middle. So this is an example of what an actual starch, which you shouldn't know. This is an example of what an actual starch molecule would look like. So just to give you an idea, this is hidden by a box. This thing over here is hidden with a box. The linkage is just an oxygen atom that's kind of bonded with or connecting, or is used as a link. So box connecting with an oxygen, box connecting with an oxygen, and you get this long chain carbohydrate. That's about it. So now right at the end, I'm just going to talk a little bit about soaps. And I'm going to talk about how soaps are produced. So soaps are, you use soap every day. That's obvious. So how are soaps produced? They're produced from the alkaline hydrolysis of fats, which are kind of a type of polyester. So you break down the polyester, which we did earlier, by alkaline hydrolysis. What happens is that the ester molecule would break down back into a carboxylic acid. The OH would be joined back. This would break down back into an alcohol, a diol. The H would come back, and it just continues. This would turn back into a carboxylic acid. So the ester kind of breaks down. The esters that we made earlier, the fat molecules that contain ester linkages, they're going to break down. And what would then happen is that when you do alkaline hydrolysis, what would happen after that is that the carboxylic acid that is produced would always react with the alkali, because obviously it's a base, and carboxylic acids are acids. So instead, what you'll get is not this molecule, you'll get a salt of this molecule. What's going to happen is that the acid would lose its H, and Na is going to replace it. That's how carboxylic acid salts were produced. So the OH would turn into O minus 1 and Na plus 1. The H would be lost, and Na plus 1 is going to take its place. So that's a salt of a carboxylic acid is known as soaps. These are your soaps. So this is what happens. And this is how soaps are created. Take fat, break them down by adding water or heating with NaOH. Uh, the carboxylic acid and the alcohols are produced back again. And once that happens, you react it with a base. You don't react it with the base, you've already added a base. They're going to get produced and they're going to react with the base anyways, if you like it or not. And they're going to turn into a salt. And the salt of a carboxylic acid is known as soaps. So that pretty much sums up our crash course on organic chemistry for specifically O levels. Make sure if you want to discuss this in detail, like this one was a very quick crash course. You want to study in detail, you can either log in and sign up at megalecture.com, or the other thing that you can do is we've got tons of detailed class lectures that are already on Mega Lecture on YouTube, and you can go and join those as well.